The corona paradox, hotter than the surface. The photosphere of the Sun, the visible and densest region of the star, maintains a temperature of around 5,500 degrees Celsius. However, just above it, instead of an expected drop in temperature, we observe a sudden increase. The solar corona, the outer and rarefied layer, reaches millions of degrees Celsius. It is a thermal inversion that challenges the classical model of heat transfer and represents one of the greatest enigmas of modern stellar physics. The low density of the corona prevents efficient thermal conduction from the photosphere. Since the medium is dominated by plasma, an ionized gas highly sensitive to magnetic fields, the mechanisms of energy dissipation follow laws different from those operating in neutral atmospheres. This forces scientists to seek explanations outside the conventional repertoire. Among the most investigated mechanisms are Alfvén waves, which transport energy along the Sun's magnetic field lines. These waves travel through spicules and fine structures that emerge from the chromosphere and can dissipate in the corona through turbulence or nonlinear effects, converting magnetic energy into heat. Recent data from the Parker Solar Probe revealed structures called switchbacks, abrupt reversals in the solar magnetic field. They indicate zones of reconnection and instability that accelerate particles and release energy in a localized manner, possibly contributing directly to coronal heating. Another strong hypothesis involves nanoflares, proposed by Eugene Parker. These are extremely small magnetic explosions, but so frequent that their cumulative effect could explain the corona's energy balance. Telescopes specialized in extreme ultraviolet have been searching for indirect evidence of these events for years. The solar magnetic field lines, highly intertwined and dynamic, form a three-dimensional mesh that stores energy. When these lines reconnect, they can release heat at specific points in the corona, contributing to localized and recurrent temperature rises. Missions like the Parker Solar Probe and the Solar Orbiter have been refining this picture. While Parker collects data directly from within the corona, the Orbiter enables remote observations that help map the magnetic structure and dynamics of the solar atmosphere with unprecedented precision. Despite progress, numerical models based on magnetohydrodynamics still diverge on the relative contribution of each mechanism. The current consensus is that coronal heating results from multiple combined processes, varying in intensity and temporal scale depending on the region and solar activity. Beyond theoretical importance, understanding this phenomenon has practical applications. The corona is the birthplace of the solar wind and coronal mass ejections, events that directly impact Earth's space environment, satellites, power grids, and communication systems. Even though it is extremely rarefied, the corona emits intensely in extreme ultraviolet and X-ray wavelengths, providing clues about its temperature, density, and composition. This radiation is constantly monitored by solar observatories in orbit. Hidden superstorms in history, Miyake events. In 2012, scientists identified a sudden spike in carbon-14 concentrations in tree rings dated to the year 775 AD. The phenomenon, independently verified across different regions of the planet, pointed to a rare and extremely energetic cosmic event. Since then, this type of occurrence has become known as a Miyake event. These abrupt increases in cosmogenic isotopes, such as carbon-14 and beryllium-10, are interpreted as signs of intense solar outbursts, with energetic particle emissions powerful enough to alter the chemistry of Earth's atmosphere. When interacting with nitrogen and oxygen molecules, these particles generate isotopes that become embedded in trees and glaciers for millennia. What makes these events remarkable is their scale. Compared to the Carrington event of 1859, long considered the most intense solar storm ever recorded, Miyake events appear to have been up to 10 times more powerful in terms of particle radiation. And unlike Carrington, there are no historical records of auroras or disturbances, suggesting a silent yet profound impact. In addition to the event of 775 AD, similar occurrences have been found in 993 AD and 660 BC, indicating that the Sun is capable of producing storms far more extreme than anything observed in the modern era. The estimated frequency of such outbursts is roughly once every 500 to 1,000 years. These episodes cannot be explained by supernovae or extrasolar sources. The isotopic signature and geographic distribution of the data clearly point to a solar origin, likely extreme-class flares accompanied by coronal mass ejections aimed directly at Earth with magnetic orientations favorable for coupling with the terrestrial magnetosphere. Computational models attempt to estimate the particle flux required to produce the observed peaks. They show that an extended energy spectrum would be necessary, capable of generating relativistic particles. This far exceeds known solar events and suggests a magnetic reconnection physics not yet fully understood. In practical terms, if such an event were to occur today, the impacts would be severe. Satellites in orbit could be damaged or destroyed, power grids would collapse, and radio communications would suffer global blackouts. Polar aviation would have to be suspended, and astronauts would face significantly increased risk. The warning time for such particles is short, from minutes to just a few hours, and current monitoring systems are not prepared for an event of this magnitude. Missions like DSCOVR, positioned at the L1 point, provide real-time data, but the response would still be limited in the face of the expected intensity. Science is now searching for new evidence in geological and biological records. Multidisciplinary projects are combining dendrochronology, glaciology, and spectrometry to identify other similar events and refine their frequency. Each new data point helps build a statistical map of extreme solar activity across millennia. Miyake events reveal a neglected facet of our Sun, its capacity to produce storms that, while rare, are potentially catastrophic. Understanding these episodes is vital not only for astrophysics, but also for protecting the technological infrastructures that underpin modern civilization. Impossible gamma rays from flares. Solar explosions, known as flares, are intense events that release enormous amounts of energy in a matter of minutes. These eruptions are typically observed in wavelengths such as ultraviolet and X-rays, but some also emit gamma rays, the most energetic form of electromagnetic radiation. What puzzles scientists is that in certain cases, this gamma ray emission lasts for hours, defying current models of particle acceleration. Even more surprising is that these emissions have been recorded even when the flare occurs on the far side of the Sun, out of Earth's direct line of sight. In theory, radiation shouldn't be able to pass through the solar disk, which raises an unavoidable question. Where are the accelerated particles that produce these ultra-high energy photons? This phenomenon still lacks a complete explanation. Solar origin gamma rays are typically attributed to interactions between accelerated protons and the solar atmosphere, producing pions that decay into energetic photons. To sustain such emission for hours, a continuous supply of energetic protons would be necessary, or a reservoir of particles confined within magnetic fields that delay their dissipation. Neither hypothesis fully resolves the mystery. One of the most studied events occurred in 2013, when the Fermi Observatory detected gamma rays lasting more than 5 hours after the flare began. Conventional models predicted emissions lasting only a few minutes at most. This case forced scientists to reassess the ability of the solar magnetic field to trap energetic particles for such extended periods, and to reconsider the structure of acceleration regions. Some researchers have proposed that the protons responsible for the radiation may be accelerated far from the flare site, possibly at shocks formed by expanding coronal mass ejections, CMEs. In this scenario, the gamma-ray emission would originate in peripheral regions of the solar atmosphere, where the protons collide with ambient matter and produce high-energy photons in a distributed and delayed manner. Another hypothesis suggests that once accelerated, particles could follow complex trajectories along magnetic field lines that wrap around the Sun. This would allow protons accelerated in one hemisphere to reach the chromosphere on the opposite side, generating secondary gamma-ray emission far from the flare's original location. However, the exact mechanisms for the confinement and transport of these particles remain poorly understood. Observations show that solar magnetic fields are highly structured and three-dimensional, with configurations that challenge the traditional simplifications of two-dimensional models. This complex geometry may favor prolonged retention of energetic particles. The SDO, RHSSI, and Fermi missions have been systematically monitoring solar gamma-ray emission and revealing events that defy expected patterns. In some cases, light curves suggest multiple acceleration phases with different populations involved. This implies the existence of continuous injection and re-acceleration processes rather than a single explosive event. Detecting these phenomena is technically challenging. Gamma rays are rare, difficult to distinguish from cosmic background noise, and require satellites with extreme sensitivity. Despite this, the growing number of documented events suggests that prolonged emission may be more common than previously thought, but was underestimated due to instrumental limitations. With the advancement of space missions and magnetohydrodynamic modeling, researchers hope to obtain more precise three-dimensional maps of the solar environment and particle trajectories. This may help to understand how energy is transported via magnetic fields between distant regions, and how this results in unexpected signals for Earth-based observers. The persistence of these gamma rays beyond expected times and locations poses a direct challenge to classical theories of solar flares. Understanding this phenomenon demands a revision of ideas about particle acceleration, confinement, and propagation in the extreme solar environment. It remains an open mystery that is redefining the boundaries of high-energy astrophysics. Touching the Sun, Parker Solar Probe. Launched in 2018 by NASA, the Parker Solar Probe represents an unprecedented milestone in solar exploration. For the first time, a space mission entered directly into the Sun's corona, crossing the boundary where solar plasma decouples from the star's magnetic field, the so-called Alphen critical surface. Metaphorically speaking, it is as if we have touched the Sun for the very first time. The primary objective of the mission is to understand the origin of the solar wind, the continuous stream of particles that escapes from the corona and fills the solar system. Although this wind has been known for decades, its acceleration remains partially mysterious. Parker aims to uncover where and how the energy of the Sun's magnetic field is converted into the motion of charged particles. During its close orbits, the probe measured abrupt disturbances in the magnetic field, dubbed switchbacks. These structures are sudden zigzags that indicate momentary reversals in the magnetic field vector. They were observed in large numbers and appear to be linked to the acceleration and modulation of the solar wind, particularly in regions near the equator. These switchbacks are surprising for their frequency, intensity, and spatial organization. Recent models suggest they may originate from magnetic field disturbances caused by deep convection or by the differential rotation of the solar surface. Ultimately, these structures help twist and launch plasma away from the Sun. The probe also revealed that the environment inside the corona is less uniform than previously imagined. Small variations in density, temperature, and magnetic field occur on spatial and temporal scales much smaller than earlier models predicted. This indicates an extremely turbulent corona, dominated by intermittent energy release processes. Another important finding was the measurement of the position of the Alphen surface. Parker showed that this boundary is neither spherical nor static. It varies according to latitude, solar activity, and even the presence of large coronal structures. On certain occasions, the probe crossed this surface and returned, providing data from both before and after the transition. The analysis of these measurements allowed scientists to estimate how the magnetic field traps or releases plasma. Release occurs when the kinetic forces of particles overcome magnetic tension. This point marks the effective origin of the solar wind, the moment when plasma breaks free from the sun. This is crucial information for understanding the formation of space weather. Parker also observed energetic particles traveling at much higher speeds than expected for regions so close to the sun. This finding suggests that acceleration occurs lower in the solar atmosphere than previously believed, possibly near the base of the corona, and may involve rapid and localized processes such as explosive magnetic reconnection. To withstand the extreme heat, the probe is equipped with a carbon composite thermal shield capable of enduring temperatures over 1300 degrees Celsius. Behind it, instruments measure electric and magnetic fields, particles, and plasma waves with unprecedented precision. The technology involved is a feat of engineering that allows the sensors to function even within the sun's atmosphere. With each orbit, the Parker Solar Probe moves closer to the sun thanks to gravitational assists from Venus that reduce its orbital speed. By the end of the mission in 2025, it will come within about 6 million kilometers of the solar surface, the closest any human-made object has ever come to a star. The Parker Solar Probe is revealing, for the first time, the internal details of the machine that generates the solar wind. Its discoveries are reshaping our understanding of energy transfer, magnetic turbulence, and plasma dynamics. By literally crossing the sun's boundary, it transforms speculation into direct observation, a qualitative leap for heliophysics. The problem of solar neutrinos. For decades, one of the greatest enigmas in astrophysics was the so-called solar neutrino problem. According to fusion models of the sun's core, a specific number of neutrinos, subatomic particles emitted during the conversion of hydrogen into helium, was expected to be detected. However, detectors were only receiving about 1/3 of the predicted amount, leaving the scientific community perplexed. Neutrinos are notoriously difficult to detect. They interact very weakly with matter, passing through entire planets as if they were transparent. Because of this, early experiments required large volumes of sensitive material, such as tanks filled with perchloroethylene in underground mines, to capture rare interactions with atomic nuclei. These pioneering experiments, like the one led by Raymond Davis Jr. in the U.S., detected neutrinos with some efficiency, but the numbers remained lower than expected. Confidence in solar models was high, suggesting the issue might not lie in astrophysics, but in particle physics. This hypothesis would eventually transform the very understanding of neutrinos. The solution came with a revolutionary idea. Neutrinos can change flavor as they travel. There are 3 types, or flavors, of neutrinos: electron, muon, and tau. Early detectors were sensitive only to electron neutrinos, but the sun emits all 3 types over the course of their journey to Earth. The issue was one of limited perception. Confirmation came from experiments like the Sudbury Neutrino Observatory in Canada. It used heavy water to detect all neutrino flavors. By comparing the totals, physicists confirmed that all the expected solar neutrinos were present. They simply changed identity along the way, a phenomenon known as neutrino oscillation. This oscillation is only possible if neutrinos have mass, however tiny. That contradicted the standard model of particle physics, which assumed neutrinos were massless. The discovery therefore demanded a theoretical revision and earned the 2015 Nobel Prize in Physics for Takaaki Kajita and Arthur B. MacDonald, who led the decisive experiments. The exact mass of neutrinos remains undetermined, but it is known to be extremely small, millions of times less than that of an electron. Still, this mass is sufficient to enable quantum oscillations between flavors. It's a collective effect involving billions of particles generated in the Sun's core. Detecting neutrinos has become a key tool in validating solar nuclear models. The proton-proton cycle, the main fusion pathway in the Sun, predicts specific neutrino fluxes with varying energies. Measuring these fluxes confirms the nuclear reactions happening 150 million kilometers away, without relying on light. Light, it's worth noting, takes tens of thousands of years to escape the Sun's interior. Neutrinos, on the other hand, exit almost instantly. They are like direct messengers from the stellar core, allowing us to observe in real time the fusion engine that sustains life on Earth. Today, facilities like Kamiokande in Japan and Boraxino in Italy continue to refine these measurements. Sensitivity has increased to the point of distinguishing fluxes from different nuclear reactions. It is a science of precision, supported by statistics involving trillions of particles detected over years. Solar astrophysics and particle physics, once distinct fields, have converged in this challenge. The Sun, in addition to being a natural fusion laboratory, has become a constant source of neutrinos for experiments probing the fundamental properties of matter and the quantum laws of the universe. Studies of solar neutrinos have also helped calibrate detectors for geophysical and cosmic neutrinos. This includes the search for neutrinos from supernovae, the cosmic background, and even exotic processes such as dark matter annihilation. In this context, the Sun serves as a reliable standard emitter. The confirmation of neutrino oscillations reinforced the robustness of standard solar models. It showed that energy production by fusion aligns with predictions, and that the observed discrepancy stemmed from instrumental and conceptual limitations. It was one of the greatest triumphs of observational science. Moreover, solar neutrinos are one of the only direct ways to study the Sun's core. Neither seismic waves nor magnetic fields penetrate that deeply. These particles carry a clear and unfiltered signature of what happens in the stellar heart, with no interference and no delay. Real-time messengers from the core. Trillions of solar neutrinos pass through every square centimeter of the human body each second, leaving no trace. These nearly massless and chargeless particles are generated in the core of the Sun during the fusion of hydrogen into helium, the fundamental process that powers the star. And because of their elusive nature, they are also the only messengers that inform us directly about what's happening deep inside. Most forms of energy produced in the Sun's core, such as light, take an immeasurable amount of time to reach the surface. A photon emitted at the Sun's center can take up to 100,000 years to zigzag through billions of collisions before emerging at the photosphere. Neutrinos, in contrast, escape in seconds and travel in a straight line to Earth. This makes neutrinos a kind of live signal of solar nuclear activity. Detecting them is like observing the heart of the star directly, something even the most powerful telescopes cannot do. These particles pass unscathed through plasma layers, magnetic fields, and internal structures, carrying information that no other form of radiation can provide. Underground detectors around the world continuously register these fluxes. Their depth is necessary to shield the faint neutrino signals from cosmic rays and background radiation. Giant tanks filled with pure water, heavy water, or other sensitive materials capture the rare interaction events with atoms, registering tiny flashes of light. The rate of these detections confirms the operation of the proton-proton chain, the Sun's main fusion pathway. But there are also secondary flows, such as neutrinos from the CNO, carbon-nitrogen-oxygen cycle, which contribute to a lesser extent. Detecting these different sources helps refine internal models of the star with impressive detail. Because they are generated in specific reactions, neutrinos carry the energy signature of those steps. This allows scientists not only to confirm that fusion is occurring, but also to determine in what proportions and under what conditions. It's like reconstructing the engine of the Sun by analyzing the exhaust, but in real time and with atomic precision. The data also show that the neutrino flux is extremely stable over time. This indicates that the Sun's interior is far more constant than its surface, where magnetic field fluctuations and sunspots are frequent. Neutrinos record the steadiness of the stellar generator, even during storms on the shell. Solar neutrinos are unaffected by external solar variations or by the Earth-Sun distance. They travel at nearly the speed of light, and their interaction with matter is so rare that even an entire planet doesn't stop them. This property makes them ideal as reliable indicators of stellar energy production. In addition to studying the Sun, neutrinos provide insights into physics beyond the standard model. Phenomena like flavor oscillation discussed in the previous topic were confirmed based on solar neutrino analysis. Thus, these particles act as a bridge between astrophysics and fundamental physics. Future experiments such as Hyper-Kamiokande in Japan and DUNE in the United States aim not only for greater sensitivity but also for more precise temporal and spectral resolution. This will allow scientists to compare subtle variations in neutrino flux with solar cycles or unusual fusion events. This could be a new form of stellar weather forecasting. These messengers have also been crucial in the study of supernovae. In 1987, neutrinos arrived on Earth hours before the visible light from a collapsing star in the Large Magellanic Cloud. This demonstrated that even on galactic scales, they remained the first to carry news of extreme energetic events. In planetary systems beyond our own, direct neutrino observation is still unfeasible. But in our case, having a natural detector just 150 million kilometers away provides an unparalleled base to test theories and calibrate instruments. The Sun thus serves as both a laboratory and a primary source at once. Nanoflares, the invisible stove. The Sun's corona reaches millions of degrees, far hotter than its visible surface, and one theory to explain this discrepancy centers on nanoflares. These are tiny magnetic explosions, far smaller than typical solar flares, that might occur by the millions across the solar atmosphere. Though individually weak, their cumulative energy could account for the intense heat of the corona. Their elusive nature, however, makes them challenging to detect directly. Nanoflares were first proposed by Eugene Parker in the late 1980s as a solution to the coronal heating problem. The concept relies on frequent, small-scale magnetic reconnection events that release bursts of energy into the surrounding plasma. Because these events are sub-resolution for most current instruments, the idea remained theoretical for many years. Yet mounting indirect evidence now supports their potential role. Observations in extreme ultraviolet and X-rays have revealed flickers of activity on very small spatial and temporal scales. These microbursts exhibit characteristics expected from nanoflares: localized heating, rapid energy release, and transient magnetic restructuring. Instruments like the high-resolution coronal imager, HI-C, and EUNIS have pushed detection closer to the required resolution. Still, distinguishing nanoflares from background noise is extremely difficult. Their signatures are often masked by overlapping emissions and the limited cadence of observations. Researchers use statistical analysis of light curves, looking for patterns consistent with frequent, low-intensity energy releases. The goal is to determine whether the observed energy flux can match the demands of coronal heating. Nanoflares are believed to originate in the tangled magnetic field lines generated by convection below the photosphere. These fields become stressed and twisted until they snap and reconnect, releasing stored magnetic energy. Unlike larger flares, nanoflares occur on small magnetic loops, often below the threshold of current image resolution. Simulations of magnetohydrodynamics support the plausibility of such events. They suggest that coronal loops are filled with constant magnetic activity at tiny scales. The cumulative heating from these reconnections could elevate plasma temperatures without the need for massive explosions. But translating theory into verified observation remains a major goal. One approach is to look for high-energy particles or spectral line broadening associated with sudden heating. Some studies report evidence of superhot plasma, above 10 million degrees, in regions without visible flares. This suggests that invisible, small-scale events may be active in energizing the corona continuously. Another promising direction involves spectroscopic analysis of emission lines sensitive to temperature and density changes. Instruments on the Solar Dynamics Observatory, SDO, and IRIS provide detailed spectral data that can hint at heating patterns consistent with nanoflare theory. Matching these to temporal and spatial data is key. The idea that the corona is not steadily heated, but instead constantly crackling with energy, aligns with the nanoflare model. Each event would be imperceptible on its own, but together they form an invisible furnace. It redefines how we think about stellar atmospheres, not as passive shells, but as active, dynamic, and turbulent systems. In addition to explaining heating, nanoflares might contribute to solar wind acceleration. The energy they release could disturb plasma and drive particles outward. This links their potential role not only to thermal balance, but also to the large-scale outflow of solar material into space. The challenge lies in capturing sufficient resolution, both in time and space, to resolve these events. Advances in solar instrumentation, such as Solar Orbiter and DKIST, aim to close this gap. Higher cadence and finer resolution will allow a deeper search for nanoflare signatures. Even if not all coronal heating is due to nanoflares, they likely play a part. Their ubiquity in models and indirect observations supports this idea. Understanding their contribution helps refine global energy models of the Sun and may reveal universal mechanisms applicable to other stars. The implications extend beyond solar physics. Similar processes might occur in stellar coronas across the galaxy, where magnetic reconnection at small scales may dominate energy transport. The Sun then serves as a nearby test case for processes that shape astrophysical plasmas broadly. While the definitive detection of a single nanoflare remains elusive, the weight of circumstantial evidence is growing. Researchers continue to refine models, improve instruments, and interpret increasingly detailed data. The hunt for the invisible stove continues. In sum, nanoflares represent a compelling, though still partially hidden, answer to one of solar physics's greatest mysteries. They embody the idea that countless tiny events, imperceptible alone, may together power the extreme outer atmosphere of our nearest star. Spicules, millions of jets everywhere. Spicules are narrow jets of solar plasma that erupt continuously across the Sun's surface, shooting upward at extraordinary speeds. These slender structures span hundreds of kilometers in width and tens of thousands in height, yet last only minutes. They occur in massive numbers, millions active at any time, forming a dense forest of dynamic motion. Each spicule rises from the chromosphere, the layer just above the photosphere, into the lower corona. Speeds typically range from 20 to 100 kilometers per second, though some reach over 150 kilometers per second. Despite their small scale and short lifespan, their sheer abundance makes them significant in the solar mass and energy budget. For decades, spicules were considered curious but inconsequential features. Early solar telescopes lacked the resolution to capture their structure in detail. However, modern instruments have revealed their complexity and hinted at a more important role in coronal heating and solar wind formation. There are two main types of spicules, classified based on their dynamics and temperature evolution. Type 1 spicules follow parabolic paths, rising and falling symmetrically. Type 2 are faster, shorter-lived, and fade without returning, likely heating rapidly to coronal temperatures and merging with the solar atmosphere. Observations from the Hinode satellite and IRIS mission have transformed our understanding of these features. They've shown that spicules can carry both mass and energy into the corona, potentially feeding the material that sustains solar wind streams. Their motion also induces waves and turbulence in magnetic field lines. Spicules often originate near regions of strong magnetic activity. Their formation seems tied to magnetic reconnection at small scales or wave interactions in the lower atmosphere. The precise trigger remains debated, but the correlation with magnetic network boundaries is well established. They can be observed in spectral lines like H-alpha and Ca2, where their vertical structure and evolution are best resolved. High-cadence imaging shows rapid heating as they rise, with some reaching coronal temperatures within seconds. This transition indicates intense energy deposition during their brief ascent. Although individually faint, the cumulative mass flow from spicules may rival that of the solar wind. Estimates suggest that they transport sufficient material to replenish the corona continually. If a fraction of them heat to coronal temperatures, they could significantly contribute to overall energy balance. Their role in generating alpha waves is also notable. As they rise and twist, they perturb magnetic field lines, launching waves into the corona. These waves may dissipate their energy and help heat the surrounding plasma, a mechanism complementary to nanoflares. Simulations of spicule dynamics require high-resolution magnetohydrodynamic modeling. These models must include partial ionization effects and radiative transfer to capture realistic behavior. Recent advances have begun to match observed properties more closely, supporting their role in upper atmospheric dynamics. Spicules exhibit regional variation, more intense and frequent near active regions, more uniform in coronal holes. This spatial pattern aligns with differences in solar wind speed and composition, linking spicule activity with heliospheric structure. Unlike larger solar phenomena, spicules operate at granular scales but interact with global processes. Their ubiquity across the Sun makes them a fundamental component of atmospheric dynamics. They serve as conduits for mass and energy exchange between the lower and upper layers of the Sun. Some researchers propose that spicules are surface expressions of deeper convective instabilities or magnetic oscillations. If true, their study offers insight into subsurface solar behavior, a window into processes occurring below the photosphere. Ongoing missions like Solar Orbiter and the Daniel K. Inouye Solar Telescope, or DKIST, aim to resolve finer details of spicule formation. These observations will help clarify their thermodynamic evolution, acceleration mechanisms, and magnetic connectivity. In conclusion, spicules are not merely solar curiosities. Their high velocity, transient heating, and global prevalence suggest a vital role in the solar atmosphere. Through their collective action, they inject energy and material upward, a quiet but constant force shaping the Sun's outer layers. Rossby waves on the Sun. Hemispheric scale patterns. On Earth, Rossby waves dominate large-scale weather patterns, bending jet streams and influencing storm tracks. A similar phenomenon has been discovered on the Sun, planetary-scale waves rippling across its surface, each spanning tens of thousands of kilometers. These solar Rossby waves, also called R-mode oscillations, shape the Sun's magnetic activity with rhythms that persist for weeks or even months. Detected through helioseismology and time-lapse imaging, these waves twist and meander through the convection zone, just beneath the photosphere. Like on Earth, they arise due to the Coriolis force, an effect of the Sun's rotation on plasma motion. But while Earth's waves guide weather, solar Rossby waves modulate magnetic flux emergence, sunspot patterns, and flare probability. Each wave crests and troughs around the Sun's circumference, moving slowly in longitude. Observations show that they drift in the retrograde direction, opposite the Sun's rotation. Some complete a circuit in roughly 120 to 200 days, depending on depth and latitude. This slow rhythm appears to set the stage for cycles of magnetic disturbances. Crucially, solar Rossby waves seem to cluster regions of magnetic activity longitudinally. Instead of sunspots emerging randomly, they appear in preferred longitudes of activity, zones influenced by the underlying wave pattern. These active longitudes may persist across multiple solar rotations, suggesting a deep organizing structure. Missions like SDO and SOHO have helped track these oscillations by monitoring sunspot emergence and subtle Doppler shifts in surface velocity. Combining surface and subsurface data reveals that these waves are rooted deep within the convection zone. They rise, twist, and interact with the overlying magnetic field as they propagate. This interaction may explain why some solar flares and CMEs occur in clusters, or why certain regions seem unusually flare-prone. The waves don't generate energy themselves, but they modulate the conditions, compressing magnetic fields, altering stress patterns, and creating pockets of instability that can erupt later. Models incorporating Rossby waves help predict the timing and location of heightened solar activity. While not yet precise enough for operational forecasts, these models improve statistical forecasts of space weather hazards. This is crucial for satellite operations, power grids, and astronaut safety. The waves also offer a window into the Sun's internal rotation and structure. By analyzing their frequency and mode structure, scientists infer properties of the deep convection zone. It's a solar equivalent of seismology, using vibrations to study layers we can't directly observe. Interestingly, the wave's presence may affect the solar dynamo, the process that regenerates the magnetic field. Their interaction with differential rotation and convective flows could regulate magnetic field polarity, influencing the overall solar cycle and its periodic reversals. While solar Rossby waves are subtler than sunspots or flares, their organizing power is immense. They act as global modulating structures, linking surface activity to internal dynamics. Recognizing their role adds a new layer of coherence to what once seemed like chaotic magnetic eruptions. Their detection also hints at similar dynamics in other stars. Large, rotating stars with convective envelopes may host Rossby-like modes that influence stellar variability. The Sun thus serves as a prototype for understanding wave dynamics in stellar interiors more broadly. Efforts continue to refine their detection and disentangle their signal from other oscillatory modes. Their low amplitude and long period make them elusive, but the payoff is significant. insights into deep solar physics, and improved understanding of long-term activity cycles. As observational techniques sharpen, particularly with helioseismology and global magnetic mapping, these waves are becoming more prominent in solar research. They represent not just a feature of solar dynamics, but a fundamental component of how the Sun organizes its own behavior. Though invisible to the eye, Rossby waves ripple across the Sun like planetary heartbeats. Each oscillation adds to the rhythm of the star's internal engine, and through their influence, we glimpse the hidden logic behind the Sun's magnetic breath. Coronal rain, inverted solar storms. At a glance, the corona seems to only emit, ejecting flares, loops, and outflows into space, but sometimes it rains back down. This phenomenon, known as coronal rain, involves hot plasma cooling rapidly and falling along magnetic field lines back to the solar surface. It's not just a curiosity, it's a diagnostic of thermal instability in the solar atmosphere. The process begins with the heating of coronal loops, arching magnetic structures filled with plasma. If heating is uneven or intermittent, some regions cool faster than others. As the plasma cools, it condenses and becomes denser, forming clumps that can no longer resist gravity. These condensations then fall, tracing arcs from high in the corona to the lower atmosphere. It resembles a waterfall in reverse. Instead of clouds precipitating from below, hot plasma rises, cools, and rains downward. The droplets, though actually searing blobs of ionized gas, travel at speeds of tens to hundreds of kilometers per second. They glow in specific wavelengths, often captured in extreme ultraviolet. Observations from instruments like IRIS and the Solar Dynamics Observatory have provided high-resolution views of these downflows. They show that the rain often forms in series, appearing as flickering strands along the same magnetic loop. Some loops experience repeated rain cycles, suggesting ongoing cycles of heating and cooling. Coronal rain is most common in active regions and post-flare loops where rapid changes in heating occur. It indicates that thermal equilibrium has broken. A region becomes radiatively unstable, losing energy faster than it's replenished. The result is condensation and eventual gravitational collapse along magnetic rails. These events are critical for diagnosing coronal heating mechanisms. The presence of rain reveals where and when heating fails, offering a natural tracer of thermal dynamics. By analyzing the timing, location, and velocity of rain strands, scientists can infer properties of the underlying energy distribution. The plasma involved typically starts at millions of degrees, but cools to tens of thousands during descent. This rapid cooling passes through temperature regimes that emit distinct spectral lines, allowing researchers to study heating and cooling rates with high precision. Coronal rain also affects mass cycling between the chromosphere and corona. It returns material to lower layers where it can be reheated and recycled. This feedback loop plays a role in regulating density and temperature in solar loops, a dynamic, self-balancing process. From a modeling perspective, simulating coronal rain requires accounting for magnetic topology, heat conduction, radiation loss, and gravity, a full thermodynamic problem. Models that replicate observed rain behavior validate the physics behind coronal stability and energy transfer. Some studies suggest that rain can trigger secondary instabilities, such as small shocks or waves in the lower atmosphere. These in turn may influence future heating events, creating a coupled feedback loop between atmospheric layers. Rain may also act as a coolant in post-flare loops, accelerating recovery after major energy releases. By efficiently draining thermal energy, it helps stabilize magnetically complex regions and prevent runaway heating. Importantly, rain strands are small-scale, often less than 1,000 kilometers across, but highly dynamic. They appear and vanish quickly, which made them hard to detect before modern high-cadence instruments. Their discovery highlights the importance of observing transient, fine-scale solar phenomena. Coronal rain has now been observed on other stars, suggesting that the underlying process is not unique to the Sun. It may be a universal consequence of magnetically confined plasma in a thermally unstable regime, a hallmark of active stellar coronae. In essence, coronal rain is the solar atmosphere's way of restoring balance. It cools, condenses, and recycles plasma with precision governed by magnetic architecture. A quiet gravitational counterpart to the Sun's more explosive outbursts. Seen from Earth, it's a fleeting phenomenon, but in those brief arcs of falling plasma, we find clues to the limits of coronal heating and the mechanisms that both sustain and restrain the Sun's fiery crown. The strange chemistry of the corona, FIP effect. The Sun's corona doesn't just defy expectations in temperature, it also behaves oddly in its chemical makeup. When we compare the elemental composition of the corona to that of the photosphere, certain elements appear enhanced. Specifically, those with low first ionization potential, FIP, like iron, magnesium, and silicon, are enriched in the corona relative to high FIP elements like oxygen and neon. This discrepancy is called the FIP effect, and it has puzzled solar physicists for decades. The effect is not small. Low FIP elements can be enriched by factors of 3 to 4 compared to their photospheric abundance. The phenomenon occurs across various regions of the corona, including active areas and quiet loops, though the magnitude can vary with solar conditions. Understanding why this happens requires diving into plasma physics and ion transport. FIP refers to the amount of energy needed to strip an atom of its first electron. Low FIP elements are more easily ionized in the chromosphere, the layer just above the photosphere. This distinction seems to be central to how elements are sorted. One theory posits that the separation occurs where ionized and neutral atoms coexist. In those layers, electromagnetic waves and forces can selectively act on ions, mostly low FIP elements, while neutrals remain unaffected. This causes preferential upward transport of those ions into the corona. In particular, alphane waves are thought to play a role in this filtering. As they propagate along magnetic field lines, they can transfer momentum to ions through the ponderomotive force. This process may accelerate certain ions more efficiently than others, enriching the upper atmosphere with specific elements. The FIP effect is not uniform across the Sun. In coronal holes, regions where magnetic field lines open into space, the effect is weak or absent. This suggests that the geometry of magnetic fields and the type of heating involved influence how elements are transported and sorted in the corona. Measuring elemental abundances requires high-resolution spectroscopy. Instruments like EIS on Hinode and SPICE on Solar Orbiter analyze emission lines from highly ionized species. These lines serve as fingerprints of specific elements and help quantify how much of each is present in different layers of the solar atmosphere. The effect is also sensitive to the solar cycle. During periods of high activity, coronal abundances show stronger FIP-related enhancements. This indicates that dynamic magnetic restructuring, such as flares and eruptions, may amplify the separation of elements during transport into the corona. Interestingly, a reverse FIP effect has been observed in some stars. In these cases, high FIP elements appear enriched instead, suggesting different wave regimes or magnetic environments. This diversity shows that the FIP phenomenon is not universal, but shaped by stellar-specific conditions. The FIP effect has practical implications for space weather. The composition of the solar wind varies depending on whether it originates from coronal holes or active regions, Knowing the elemental ratios helps identify the source region of solar particles and understand their transport through the heliosphere. This unusual chemical sorting challenges the assumption that the corona is a simple extension of the photosphere. Instead, it acts as a selective filter, one that highlights the role of wave-particle interactions and magnetic field dynamics in shaping solar chemistry. Ongoing research uses solar wind samples, X-ray spectroscopy, and in situ measurements from missions like ACE and Solar Orbiter. These data are helping to refine models that simulate ion acceleration and element fractionation in the solar transition region and corona. Despite progress, no single model fully explains the magnitude and variability of the FIP effect. The interplay between waves, plasma state, field geometry, and atmospheric layering remains complex. It is an open question at the frontier of heliophysics. Understanding the FIP effect will improve our knowledge of how stars separate and redistribute elements in their outer atmospheres. It's a rare example of a chemical fingerprint shaped not only by temperature, but by electromagnetic environments and ionization thresholds. Ultimately, the strange chemistry of the solar corona is a reminder that even familiar elements can behave unexpectedly when subject to the sun's extreme magnetized environment. The corona doesn't just glow, it selects. Seeing the far side of the sun with sound. We cannot see the far side of the sun directly. Its vast body hides half its surface from Earth at any moment. But through a technique known as helioseismology, we can hear what we cannot see. This method uses acoustic waves traveling inside the sun to infer structures on its far side, much like sonar maps unseen seafloors on Earth. The sun constantly vibrates with millions of sound-like oscillations caused by turbulent convection near its surface. These pressure waves travel through the solar interior, bouncing and refracting depending on local conditions. Some waves emerge on the visible side after having passed through active regions on the hidden side. By analyzing these patterns with sensitive Doppler measurements, scientists can reconstruct maps of active regions, like sunspot groups, on the far hemisphere of the sun. These reconstructions provide early warnings, days in advance, of activity rotating into view. The method relies on detecting subtle changes in wave travel times. Active regions, being magnetically and thermally different, alter how waves move through them. The presence of such a region slows or deflects wave propagation, producing detectable timing anomalies at the surface. This time-distance helioseismology requires high-cadence, high-resolution data. Instruments like the Helioseismic and Magnetic Imager, HMI, aboard the Solar Dynamics Observatory, SDO, provide continuous, full-disk Doppler images of the sun's surface velocity field, which are then processed to infer internal and far-side structures. Though the reconstructions are lower in resolution than direct images, they are remarkably accurate in identifying major active zones. This has practical value for space weather forecasting. By knowing where large sunspot groups are, even when invisible, scientists can anticipate potential flares and coronal mass ejections. The method also allows tracking of long-lived active regions as they rotate in and out of view. Some active zones persist over multiple rotations, and their reappearance can be forecast based on helioseismic signatures. This extends the predictive horizon beyond what imaging alone can offer. The Farside maps are updated daily and include indicators of magnetic strength and activity trends. These data support operational models used by space agencies and researchers to assess solar risk to satellites, power grids, and astronauts. In addition to Farside imaging, helioseismology maps subsurface flows like meridional circulation and zonal flows, which help model the solar dynamo. This contributes to understanding the large-scale patterns that govern sunspot formation and the solar cycle. Similar to Earth seismology, helioseismology interprets wave reflections and refractions to reveal hidden layers. But in the solar case, the ground is plasma, and the waves are acoustic modes shaped by gravity and pressure gradients. It's an acoustic probe of stellar interiors. Variations of the technique have even revealed giant Rossby waves and internal shear layers. These findings show that the Sun's interior is not uniform, but highly structured, with dynamic patterns that influence surface behavior over months and years. Helioseismology also validates models of stellar structure. Since the Sun is the only star we can observe in such detail, these techniques help test theories that apply to other stars using a well-calibrated local example. It's a foundation for astroseismology, the study of vibrations in other stars. Improved instrumentation and algorithms continue to refine the fidelity of Farside maps. As missions like Solar Orbiter provide different vantage points, data fusion from multiple spacecraft may yield full 360-degree coverage with higher precision than ever before. The shape of our space bubble, the heliosphere. The Sun constantly emits a stream of charged particles known as the solar wind, which inflates a vast bubble around the solar system called the heliosphere. This magnetic shield protects us from a significant portion of galactic cosmic rays. For decades, it was assumed to resemble a comet, round at the front with a long tail trailing behind. But recent data suggest the reality is more complex. Observations from the Interstellar Boundary Explorer, IBEX, and the Voyager spacecraft have challenged the comet analogy. Instead, some models now suggest a croissant or bubble with lobes shape, molded not only by the solar wind but by the interstellar magnetic field. This revision changes how we understand the Sun's interaction with its galactic environment. Voyager 1 and Voyager 2 crossed the heliopause, the boundary between solar and interstellar space, in different directions and at slightly different distances. Their measurements of particle flux and magnetic fields hint that the heliosphere is asymmetrical. This contradicts older models that predicted a neat, elongated tail. The structure of the heliosphere depends on a balance of forces: the outward pressure of the solar wind, the inward push of the local interstellar medium, and the shaping effect of the galactic magnetic field. Together, these factors create a dynamic, ever-changing envelope that surrounds all planets and extends far beyond Pluto. IBEX maps energetic neutral atoms, or ENAs, formed when solar wind particles collide with interstellar atoms. These ENAs give indirect clues about the shape and density of the heliospheric boundary. They revealed a bright ribbon of emissions not predicted by any model, which suggests a magnetic alignment rather than a simple bow shock. This ribbon is believed to mark a region where interstellar magnetic fields align with the boundary of the heliosphere. Its discovery forced scientists to re-evaluate long-standing ideas about the Sun's outermost frontier. It also suggests that magnetic geometry, not just plasma pressure, determines the heliosphere's contours. The new croissant model proposes that jets of solar wind escape along the poles and wrap back, forming twin lobes. This is unlike a continuous tail. Rather, the heliosphere may be compact and pressure-balanced, with only short extensions along the solar equator. It's a shield shaped more by magnetism than by motion. Understanding the heliosphere's shape matters because it regulates how much cosmic radiation enters the inner solar system. Its geometry affects which regions are more exposed during different phases of the solar cycle. It also influences the trajectories of cosmic rays and interstellar dust. The outer edge of the heliosphere, called the heliopause, is not a static boundary. It pulses and shifts with solar activity, expanding during strong solar wind phases and contracting during quiet periods. This breathing motion adds complexity to the structure's shape and function. NASA's upcoming Interstellar Mapping and Acceleration Probe, IMAP, aims to improve our understanding of this region. IMAP will map ENAs with higher resolution and help clarify the interplay between solar and interstellar forces. It may confirm or refute the croissant model with greater precision. The shape of the heliosphere also impacts the interpretation of interstellar probe data. Voyager's readings must be adjusted for local geometry. Understanding where each probe crossed the boundary helps contextualize its measurements. This makes shape modeling essential for data analysis. Beyond Earth, planets like Uranus and Neptune experience changing shielding conditions depending on their position relative to the heliosphere's structure. Long-term cosmic ray exposure varies with heliospheric asymmetry, influencing space weather even in the outer solar system. The heliosphere is the Sun's fingerprint on the galaxy, a vast magnetized imprint marking the star's sphere of influence. As the Sun moves through the Milky Way, this bubble interacts with different interstellar environments, changing shape and properties over time. Studying its form gives us a glimpse of how stars in general protect their planetary systems. Stellar wind bubbles are likely common throughout the galaxy, but each will be sculpted uniquely by its star's wind and the local galactic conditions. The Sun's version is just one example among billions. Predicting the magnetic orientation of a CME. Coronal mass ejections, or CMEs, are massive expulsions of plasma and magnetic field from the Sun's corona. When aimed at Earth, they can trigger geomagnetic storms that disrupt satellites, power grids, and communications. But not all CMEs are equally dangerous. What matters most is the magnetic orientation of the cloud when it arrives. If the CME's embedded magnetic field is aligned northward, it tends to glide past Earth's magnetic field with little interaction. But if it's southward, it can connect with Earth's magnetosphere and inject energy into the system. This can lead to auroras, or blackouts, depending on the intensity. Forecasting this orientation is crucial. Unfortunately, predicting the internal magnetic structure of a CME before it reaches Earth remains one of the biggest challenges in space weather science. Current methods track the speed, size, and direction of CMEs using coronagraphs and heliospheric imagers, but the internal field configuration is largely unknown until impact. This is because CMEs twist and evolve as they travel through interplanetary space. Their original magnetic configuration, often a flux rope with helical field lines, can rotate, shear, or distort due to interactions with the solar wind or background fields. The structure that leaves the Sun may not match what arrives at Earth. Some missions attempt to infer magnetic orientation based on the CME's source region. If a CME originates from a well-mapped active region, magnetograms can estimate the polarity of the erupting flux rope. But even so, these inferences are uncertain, especially if the CME undergoes rotation en route. Stereo and SOHO have improved our ability to view CMEs in 3D. helping assess their trajectory and shape. But without direct measurements of internal fields, models must rely on assumptions about flux rope behavior. This limits the accuracy of forecasts for orientation-sensitive effects. NASA's upcoming mission, Solar-C EUVST, and instruments on Solar Orbiter may offer new diagnostics of CME formation, including early signatures of magnetic twist. Meanwhile, real-time in situ measurements are only possible with satellites stationed upstream, like ACE or DSCO-VR at L1. These upstream monitors provide about 15 to 60 minutes of warning for the magnetic orientation. That's enough for short-term responses, but insufficient for broader infrastructure mitigation. Knowing the orientation 1 or 2 days in advance remains the goal and the frontier. Improving this requires better models of CME initiation, especially the structure and twist of flux ropes as they lift off. Coupling these with solar surface observations and coronal magnetic field extrapolations may offer more robust predictions, but uncertainties remain high. Some researchers propose deploying a constellation of satellites between the Sun and Earth, spaced in orbit to provide early magnetic profiles of approaching CMEs. These space weather sentinels could deliver multi-point field measurements and improve lead time for orientation forecasts. Until such systems are realized, we rely on statistical indicators. For example, CMEs from certain solar quadrants are more likely to rotate southward during transit. Combining this with source magnetograms and flare orientation may give probabilistic guidance, not exact predictions. The impact of magnetic orientation isn't limited to power grids. It also affects radiation exposure for high-latitude flights and astronauts, satellite drag and anomaly rates, and the efficiency of radio communications. It's the deciding factor between minor disturbance and major disruption. Auroras are one visible outcome of magnetic reconnection between Earth and southward CMEs, but less visible consequences include current surges in long pipelines, GPS errors, and increased satellite collision risk due to atmospheric expansion. All depend on field alignment at arrival. Accurate prediction of CME orientation would mark a breakthrough in operational space weather forecasting. It would transform how agencies prepare for solar storms and reduce the vulnerability of modern technology to solar activity. In the meantime, research continues, in labs, in models, and in orbit. The day we can forecast not just when a CME will arrive, but how it will strike magnetically, will be a milestone in our understanding of the Sun-Earth connection. The sunspot butterfly pattern that sometimes vanishes. The solar cycle isn't just a rhythm of rising and falling activity. It also reveals itself spatially. Sunspots, which mark regions of intense magnetic activity, don't appear randomly across the solar surface. Instead, they follow a distinct migratory pattern, starting at mid-latitudes and drifting toward the equator as the cycle progresses. This migration, when plotted over time, creates the famous butterfly diagram. Each wing corresponds to a solar hemisphere, and the wings spread downward over time. The pattern is a visual fingerprint of the solar dynamo at work, the process that generates and reorganizes magnetic fields inside the Sun. But in some cycles, the wings of the butterfly shrink or disappear entirely. During these times, sunspot activity becomes highly suppressed or shifts to unusual latitudes. These irregularities are not just aesthetic curiosities, they reflect profound changes in the inner workings of the solar magnetic engine. The butterfly pattern arises from the emergence of toroidal magnetic fields, generated in the Sun's interior and brought to the surface by convection. Their systematic equatorward drift is thought to result from the interplay of meridional circulation, differential rotation, and convective motions. When this circulation is altered, or the toroidal field is weak, sunspots fail to form or emerge in the expected locations. This breaks the butterfly pattern, signaling that the underlying dynamo process is disrupted. It's a diagnostic tool for studying the health and consistency of solar cycles. Data from observatories like Mount Wilson and satellite missions like SOHO and SDO help map this pattern across multiple cycles. High-resolution magnetograms track the birth and movement of sunspot groups, revealing shifts in migration speed, intensity, and symmetry between hemispheres. Asymmetries between hemispheres are common. One side of the Sun may begin its butterfly wing earlier or more strongly than the other. These imbalances can persist across cycles and may contribute to long-term modulations in solar activity. The Sun, it seems, does not always act in perfect unison. The butterfly pattern is also connected to polar field reversals. As sunspots emerge, their decay contributes magnetic flux to the poles. This builds the seeds for the next cycle. If the butterfly pattern falters, the polar fields may remain weak, delaying or suppressing the next cycle altogether. Studying cycle 24, scientists observed a narrower and less populated butterfly diagram. This cycle was among the weakest in a century and followed a period of unusually quiet solar conditions. The butterfly's reduced spread reflected the overall decline in magnetic field strength and emergence. Looking further back, historical records show other times when the butterfly was stunted. These include periods of low sunspot counts in the early 19th century and other minor downturns. Each instance hints at variations in the dynamo's efficiency and organization. Some solar models suggest that chaotic fluctuations in the Sun's deep interior, particularly in the tachocline, can cause these irregularities. The dynamo process may be sensitive to small shifts in flow patterns or field alignments, leading to intermittent breakdowns in sunspot production. The butterfly diagram remains a powerful visual and analytical tool. It combines time, latitude, and magnetic field into a single picture, offering insights into the Sun's cyclical behavior and its deviations. When the pattern disappears, it's not just a loss of symmetry, it's a signal of systemic change. In the absence of sunspots, the solar surface appears deceptively calm. But the internal magnetic field may still be active, just in configurations that don't breach the surface. This decoupling between internal and surface magnetism adds complexity to the interpretation of the cycle. Recognizing why the butterfly sometimes vanishes requires linking internal solar physics to surface manifestations. It's a bridge between helioseismology, dynamo theory, and long-term observational records. Each broken wing teaches something new about solar memory and variability. Grand minima and climate, example, Maunder minimum. Between 1645 and 1715, sunspot records show an extraordinary decline in solar activity, an event now called the Maunder minimum. During this 70-year interval, only a few sunspots were recorded, and the usual 11-year solar cycle became faint or vanished entirely. This was not just a quiet spell, but a grand minimum. Grand minima differ from ordinary low cycles in duration and depth. While typical solar cycles vary in amplitude, grand minima involve multiple decades of suppressed activity. They reflect a long-term disruption in the solar dynamo, not just one weak cycle, but a persistent breakdown in magnetic field generation. Ice core data, tree rings, and historical auroral records all corroborate this anomaly. The decline in solar activity coincided with colder periods in the northern hemisphere, including the so-called Little Ice Age. Though the causes of this climate cooling were multifactorial, reduced solar irradiance played a contributing role. During the Maunder minimum, temperatures dropped in parts of Europe and North America. Winters became longer and harsher, glaciers advanced, and crop failures increased. The River Thames in London froze frequently, and records from the time describe famines and socioeconomic stress linked to climate variability. It is important to distinguish between total solar irradiance and ultraviolet output. While the sun's total energy output varies only slightly during cycles, about 0.1%, the change in UV radiation is much more pronounced. UV affects stratospheric ozone and atmospheric circulation, amplifying small solar variations. The connection between grand minima and climate is still debated. Climate systems are influenced by volcanic activity, oceanic cycles, greenhouse gases, and more. But correlations between low solar activity and regional cooling suggest that the sun exerts a subtle but measurable influence on Earth's climate system. Reconstructions using beryllium-10 and carbon-14 isotopes reveal that the sun has entered grand minima many times over the last 10,000 years. The Maunder minimum is just the most well-documented. Other events, like the Sporer minimum, 1460 to 1550, and Dalton minimum, 1790 to 1830, show similar patterns. These records indicate that the solar dynamo can fluctuate over centennial timescales. Magnetic activity, while generally regular, is modulated by stochastic and possibly chaotic processes in the sun's interior. This suggests that grand minima are intrinsic features of solar behavior, not anomalies, but natural variations. Models of the solar dynamo now include parameters for magnetic memory, stochastic noise, and flow instabilities. These features can spontaneously produce periods of weak or vanishing cycles consistent with grand minima. Still, predicting when such phases will recur remains beyond current capabilities. During grand minima, the heliosphere contracts slightly, reducing shielding from galactic cosmic rays. This affects atmospheric chemistry and increases radiation levels on Earth. Ironically, a quieter sun allows more cosmic activity to reach our planet, a reminder that space weather continues even in solar silence. Satellites and modern electronics were not around during the Maunder minimum, so we don't fully know how such a prolonged quiet phase would affect current technology. But the increased cosmic ray flux could raise risks for electronics, avionics, and human health in space. Some scientists worry that a future grand minimum could mask or interact with anthropogenic climate change. However, even a strong minimum would likely only produce a modest global cooling, insufficient to offset warming trends, but still relevant for understanding regional climate variability. The sun has since recovered from the Maunder minimum, resuming its 11-year cycle with varying intensity, but the possibility of future minima remains. Monitoring polar fields, sunspot trends, and internal flows may offer clues, though lead time for prediction remains limited. In historical context, the Maunder minimum shows that the sun is not a metronome. Its rhythm is complex, capable of deep pauses and shifts.
These pauses leave imprints on climate, history, and civilization, subtle signs of our dependence on stellar regularity. Understanding grand minima is part of a broader effort to grasp solar variability. By studying these quiet epochs, we learn not only about solar physics, but about how sensitive Earth's systems are to even small celestial changes. The sun doesn't have to roar to make itself felt.
Superflares on solar twins. The sun, though dynamic, seems relatively mild compared to some of its stellar relatives. Observations from space telescopes like Kepler and TESS have revealed that many sun-like stars, known as solar twins, can produce superflares. These are colossal eruptions, releasing hundreds to thousands times more energy than the most powerful solar flares we've seen. Superflares on these stars are not just rare outbursts. In some cases, they occur on stars with similar mass, temperature, and rotation to our Sun. This raises a crucial question. If these stars can erupt violently, why doesn't our Sun do the same? Or has it, and we just haven't seen it in the modern era? Data suggest that superflares are more common on younger, faster-rotating solar-type stars. Faster rotation enhances the stellar dynamo, the process that generates magnetic fields, making their outer atmospheres more magnetically active. This could partly explain the difference. However, some superflares have been recorded on stars with rotation periods and spectral types very close to the Sun's. This blurs the line between active and quiet stars and challenges the assumption that the Sun is fundamentally different. Our star may be in a phase of unusually calm behavior. If the Sun were to emit a superflare, the consequences would be severe. Modern infrastructure, satellites, power grids, communication systems could suffer catastrophic damage. The Carrington event of 1859 is often cited as a reference point, but even that pales in comparison to true superflares. Estimates from tree ring records and ice cores, particularly the so-called Miyake events, hint that stronger solar outbursts may have occurred in pre-industrial times. These leave chemical signatures, such as increased carbon-14, that suggest sudden influxes of high-energy particles. While the Sun's current behavior seems stable, these findings imply it may not be immune to superflares. The long intervals between such events, perhaps centuries or millennia, mean our observational window is limited. We may simply be living in a quiet interlude. Understanding what triggers superflares in Sun-like stars is essential. The interplay between magnetic field strength, complexity, and surface rotation appears to be key. Some models suggest that tightly braided magnetic loops can store and release vast amounts of energy under the right conditions. Starspot coverage is another clue. Solar twins that emit superflares often show evidence of large, persistent star spots, some covering 10% of the stellar surface. These giant magnetic regions are thought to anchor and stabilize the magnetic energy buildup required for superflares. Spectroscopic observations of these stars during flares reveal high-energy emissions across the UV, optical, and X-ray bands. The light curves show rapid rises and gradual decays, much like solar flares, but scaled up dramatically. The underlying processes may be similar, but with more fuel. This research is not purely academic. As we plan long-term space missions and develop dependence on satellite networks, understanding the limits of solar behavior becomes a matter of risk assessment. If the Sun can produce even a modest superflare, our preparedness matters. Solar monitoring now includes searches for high-frequency pulsations, flare precursors, and magnetic field instabilities. Missions like Solar Orbiter and DKIST contribute high-resolution data that may one day identify early signs of unusual activity. For now, the Sun remains within familiar bounds. Still, nature doesn't guarantee permanence. The dynamo that powers solar magnetism is inherently chaotic. Just because we haven't seen a superflare in recent centuries doesn't mean it can't happen again. The evidence from stellar twins keeps the possibility open. Understanding superflares in the context of stellar evolution also helps us calibrate what to expect from stars at different ages. The Sun's current quiet phase may reflect its middle-aged status, but not necessarily its limits. The story remains incomplete without longer-term data. The study of superflares on solar twins is a window into the potential extremes of stellar magnetism. It invites us to question what is typical, what is exceptional, and what risks may lurk beneath even the calmest solar surface. When stars that resemble ours misbehave, we pay attention. Sunquakes, solar quakes. While the Sun lacks a solid crust, it still experiences seismic events. These sunquakes, rippling shock waves across the solar surface, are triggered by the intense magnetic explosions known as flares. They behave like stellar analogs of earthquakes, but instead of shaking ground, they shake plasma. Sunquakes were first confirmed in 1996 when researchers observed acoustic waves radiating from a flare site using data from SOHO. The waves resembled concentric rings on water, expanding rapidly outward across the photosphere. Their speed, amplitude, and symmetry revealed their seismic nature. The shockwave originates deep in the solar atmosphere and punches downward into the dense layers of the photosphere. From there, it spreads outward at speeds exceeding 100,000 kilometers per hour. The resulting ripples are subtle, but detectable with Doppler imaging and helioseismic analysis. These quakes are associated with sudden, intense impacts, often occurring milliseconds after a flare's peak. The exact trigger remains debated. Some theories point to the rapid reconfiguration of magnetic fields, others to accelerated particles delivering kinetic energy to the lower atmosphere. Flares release energy not just upward into the corona, but also downward. This downward energy may be sufficient to compress the solar surface, launching acoustic waves. The amplitude of these waves varies with flare strength and depth of energy deposition. Some sunquakes have been analogized to 11.3 on the Richter scale, a staggering release of energy, though applied to plasma, not rock. The motion isn't visible to the eye, but instruments like HMI on SDO track it through velocity shifts and brightness oscillations. Not all flares generate sunquakes. Those that do tend to be more impulsive and energetic. The presence of magnetic shear and rapid energy release seems to be a factor, but the exact conditions required remain under study. Sunquakes are relatively rare compared to the total number of flares. Mapping sunquake sources helps locate regions of intense magnetic stress. These are areas where stored magnetic energy is most likely to be explosively converted into heat, light, and motion. Sunquakes are thus not just seismic features, they're diagnostics of energy flow. They also offer insight into the solar interior. As waves propagate, they interact with subsurface structures. By analyzing travel times and deflections, scientists can infer details about the Sun's internal composition, making sunquakes a tool of local helioseismology. Advanced simulations now attempt to reproduce sunquakes by modeling the energy deposition of flares and particle beams. These studies help connect observed seismic signatures with flare physics, offering a more complete picture of the flare-quake mechanism. Sunquakes contribute to the broader field of space weather research. While they pose no direct risk to Earth, their connection to powerful flares and CMEs makes them relevant as indicators. A quake may signal that a region has released its stored energy or that more is yet to come. The spatial pattern of sunquake waves, their symmetry, speed, and dispersion reveals subtle details about the photospheric layers. It's an acoustic probe of the Sun's outer shell, complementing deeper helioseismic measurements that trace waves through the solar interior. With advanced instrumentation, more sunquakes are being detected. Their small amplitude makes them easy to miss without high temporal and spatial resolution. Missions like Solar Orbiter may soon add new vantage points for capturing these fleeting seismic events. In the language of stellar physics, sunquakes are the echoes of violence. They are brief, powerful signatures of the magnetic tensions building and snapping on the solar surface. In a star with no solid crust, even the sound of motion is born through plasma. Solar tsunamis are immense waves of plasma that surge across the sun's surface following major eruptions. First observed in detail by SOHO in the late 1990s, they travel at hundreds of thousands of kilometers per hour, expanding outward like shock waves. Despite their name, they are not related to oceanic processes. They're magneto-hydrodynamic waves in a star. Also known as EIT waves, these phenomena were initially considered rare, but with modern imaging from SDO and Solar Orbiter, we now know they occur more frequently, often accompanying large flares and CMEs. They sweep across the corona, sometimes spanning the entire solar disk within minutes. These waves are not gentle ripples. They compress, heat, and perturb everything in their path. As they travel, they can trigger oscillations in coronal loops, rearrange magnetic field lines, and even launch secondary eruptions. Their energy and momentum are signatures of massive reconfigurations in the solar atmosphere. Solar tsunamis are often linked with CME initiation. As the CME lifts off, it pushes against the surrounding magnetic environment, driving the wave ahead of it. This causes a rapid expansion of plasma and magnetic field, a kind of stellar bow shock. Observing the wave helps scientists estimate the CME's energy. The wave front typically appears as a bright arc in extreme ultraviolet EUV wavelengths. Behind it, coronal dimming may follow, a region where plasma has been evacuated. The wave's speed and direction offer clues about the ambient magnetic field structure and plasma density. Not all solar tsunamis are identical. Some are fast-mode magnetosonic waves, true physical compressions. Others may be pseudo-waves, created by the restructuring of magnetic fields rather than by propagating pressure. Distinguishing between them requires high-cadence, multi-wavelength data. The fastest solar tsunamis can reach speeds exceeding 1,000 kilometers per second. These are associated with particularly energetic flares and CMEs and often herald strong space weather events. Slower waves may still carry important information about local conditions in the corona. By analyzing the wave's behavior as it crosses different solar regions, researchers can map coronal properties like magnetic field strength, plasma temperature, and density gradients. Solar tsunamis are thus diagnostic tools for probing the sun's outer layers in real time. Some solar tsunamis trigger sympathetic events, eruptions or brightenings in distant regions. These chain reactions suggest that magnetic stress and energy redistribution can propagate across vast distances. The solar surface is not isolated, it's a connected, dynamic system. Observations from multiple angles, such as with stereo, allow 3D reconstruction of these waves. This reveals their height above the surface, their curvature, and their interaction with solar structures. Understanding their geometry improves CME forecasting and flare diagnostics. Solar tsunamis also interact with polar plumes, coronal holes, and active regions. These features can reflect, refract, or absorb parts of the wave. Studying such interactions helps refine coronal models and test simulations of wave propagation in magnetized plasma. Despite their violent nature, solar tsunamis pose no direct threat to Earth. However, because they're tightly coupled with CMEs and flares, they serve as important early indicators of eruptive events. Real-time detection is a tool for space weather monitoring. Machine learning tools are now being trained to recognize these wavefronts in solar data streams. Automated detection could improve the response time of space weather alert systems, particularly when used in conjunction with CME tracking and flare analysis. The physics of solar tsunamis bridges plasma physics, magnetohydrodynamics, and solar dynamics. They demonstrate how a single event, a flare or CME, can ripple across an entire star, unleashing energy on scales difficult to replicate or observe elsewhere. As our imaging resolution and cadence improve, we will likely uncover finer structures within these waves. Beneath the sweeping arcs, localized compressions, shocks, and current sheets await discovery. The tsunami is only the surface of a deeper story in solar physics. Flux ropes and magnetic twists. Flux ropes are tightly wound bundles of magnetic field lines, coiled like springs within the sun's atmosphere. They store vast amounts of magnetic energy, and when destabilized, they can drive solar eruptions, such as flares and coronal mass ejections. These structures are fundamental components of solar magnetism. A flux rope forms when magnetic loops become twisted by differential rotation, shearing motions, or emerging magnetic flux. As twist accumulates, the structure becomes more helical. If the magnetic tension and pressure reach a critical point, the flux rope can erupt, releasing its stored energy explosively. In some cases, the flux rope remains stable for hours or days before erupting. This metastable state allows for careful observation. Instruments like SDO's AIA and Hinoday's XRT captured these structures in the corona, often appearing as dark filaments or glowing arches suspended above the surface. The eruption of a flux rope is often preceded by the formation of a sigmoid, an S-shaped region visible in X-rays or EUV. This shape signals a highly sheared and twisted field configuration, primed for release. When the rope breaks free, it may power both a flare and a CME. Magnetic reconnection is key to this process. As the rope rises, it stretches the overlying magnetic field. When the field lines snap and reconnect below the rope, they form flare loops and simultaneously accelerate the rope upward. This is the standard CSHKP eruption model. The twisted structure of a flex rope can sometimes be preserved in CMEs. Observations from coronagraphs and in situ detectors show magnetic clouds in interplanetary space that match the expected helical profiles. These clouds carry the magnetic signature of the eruption source. The amount of twist or helicity in a flux rope influences its stability. Too little and the rope may collapse or fade. Too much and it becomes unstable to kink or torus instabilities. These instabilities govern when and how the rope erupts and what direction it takes. High-resolution vector magnetograms from instruments like HMI reveal the footprints of flux ropes in the photosphere. They show patterns of magnetic shear, current density, and polarity inversion lines, the surface roots of the complex 3D structure above. Flux ropes are also involved in failed eruptions. Sometimes the rope rises but is held down by the overlying magnetic arcade. These partial eruptions provide clues about the strength and orientation of restraining fields. They help explain why not every active region leads to a CME. Flex ropes are ubiquitous, found not just in the Sun, but in planetary magnetospheres, laboratory plasmas, and even astrophysical jets. Their dynamics are governed by fundamental principles of plasma physics, making them a unifying structure across scales and environments. The study of flux ropes helps predict solar eruptions. By monitoring magnetic twist and shearing motions, scientists can assess eruption likelihood. Automated algorithms now track flux rope indicators in solar magnetogram data to improve flare and CME forecasting. Some theories propose that flux ropes exist even before they become visible, forming beneath the photosphere and emerging as coherent, twisted structures. This emergence process may carry signatures detectable by helioseismic methods or subsurface modeling. Solar filaments are often manifestations of flux ropes seen edge-on. These cool, dense structures hover in the corona supported by magnetic tension. When they erupt, they reveal the inner helicity of the rope, traced by plasma motion and filament rotation. The alignment of a flux rope's axis and magnetic direction affects its geo-effectiveness. If Earth is struck by a CME carrying a southward-aligned flux rope, magnetic reconnection is enhanced, increasing the risk of geomagnetic storms and auroral activity.
Jupiter-sized coronal loops. The Sun's surface is crisscrossed by plasma structures that create luminous arcs on colossal scales. These coronal loops are the visible manifestation of magnetic field lines that emerge and reconnect in the photosphere. Some of these arcs reach such vast dimensions that the entire Jupiter could easily fit inside them. These structures are not only immense, they are also thermally extreme. The plasma within the loops can reach millions of degrees Celsius, sustained by magnetic containment. Their shape reveals the invisible architecture of the solar magnetic field, converting an abstract concept into something instruments can directly record. Loops connect regions of opposite magnetic polarity on the solar surface. When magnetic fields reconfigure after flares or flux surges, these arcs form as a direct consequence of the energetic rearrangement. Each loop is a signature of the solar dynamo's dynamics in action. With extreme ultraviolet images captured by probes like SDO, these arcs can be seen with stunning clarity. They appear as fluorescent bands traversing the solar limb, displaying variations in temperature, density, and cooling time along their length. Loops range from small, short-lived structures to monumental arcs that persist for hours or days. In active regions, they can overlap into complex plasma forests, tracing fields tens of thousands of kilometers high. They are the topography of solar magnetism. The shape and brightness of the loops allow us to infer physical processes such as thermal conduction, radiation, and mass circulation. Magnetohydrodynamic models attempt to reproduce their behavior, but the challenge is significant. The Sun combines complex geometry, turbulence, and variations on scales ranging from seconds to days. When heated by processes such as nanoflares or magnetic waves, the loops glow brightly in certain bands of the ultraviolet spectrum. This provides a spectroscopic window for measuring the composition and energy states of the confined plasma. Over time, the loops expand, oscillate, or collapse, reflecting changes in the field that sustains them. Transverse oscillations, for example, help estimate the plasma density and the strength of the local magnetic field. Each movement is a clue to the internal conditions. The geometry of the loops also affects energy transport. Heat generated at their base can be conducted to the top, cooling through radiation or convection. Understanding this transfer is vital to deciphering the mechanism that keeps the corona hotter than the surface. Giant loops tend to emerge after large flares. In these cases, the reconnected magnetic field forms long, stable arcs, while cooled plasma accumulates in their lower reaches. Sometimes gravity pulls this material back in, a phenomenon known as coronal rain. The topology of loops allows us to map regions of magnetic stress,
In areas with many interlocking structures, the chance of explosive reconnections increases. Therefore, loops are not just consequences, they are precursors to potential eruptive events. Even on smaller scales, these structures follow similar laws. From the smallest arc to the size of Jupiter, they all obey the principles of confined plasma physics. This allows us to use the Sun as a laboratory to understand phenomena in stars and Earth's magnetic fuses. Advanced simulations have been able to reproduce loops with increasing fidelity, including dissipation effects, instabilities, and plasma feedback in the field. But it remains difficult to model all the scales involved, especially when loops interact with waves or jets. Statistical studies of loops also reveal patterns. Correlations exist between their size, duration, emission intensity, and location in the solar cycle. These patterns help us understand the evolution of active regions and their contribution to the corona's energy balance. Ultimately, coronal loops are ephemeral sculptures sculpted by solar magnetism. They are visible traces of the invisible engine that governs stellar activity. Measuring their shape, temperature, and evolution is a way to observe the magnetic field writing in the plasma. CME, a mass Everest launched into space. Coronal mass ejections, or CMEs, are some of the Sun's most energetic manifestations. During these events, billions of tons of plasma are hurled into space at speeds exceeding 1,000,000 kilometers per hour. In terms of mass, they're equivalent to launching a mountain like Mount Everest. These eruptions occur when large magnetic structures, such as flux ropes, become unstable and collapse. The energy stored in the twisted fields is explosively released, propelling ionized plasma beyond the corona and often out into the inner heliosphere. The mass and speed of a CME determine its potential impact. When directed toward Earth, they can interact with the planetary magnetic field and cause geomagnetic storms. The orientation of the field carried by the cloud, especially if it is southerly, determines the severity of the effects. Images captured by coronagraphs, like those on SOHO and stereo, revealed the CME as a bright bubble that expands rapidly after the event. The so-called halo effect is often observed, a sign that the ejection is heading toward Earth. CMEs are often associated with flares, but not always. There are cases of silent ejections in which magnetic instability builds slowly until it reaches a critical point. In these cases, the CME may occur without significant radiation emission. The expelled plasma may contain protons, electrons, and nuclei of elements such as helium and iron, all embedded in a coherent magnetic field. As it moves, this structure interacts with the solar wind and can accelerate additional particles. Detectors in orbit and on the ground track SCME signals in real time. Probes at L1, such as ACE and DESCO, measure the magnetic field and plasma density before they reach Earth. This early warning allows for the calculation of the expected storm intensity. The impact of a CME can last for hours or days. In addition to intense auroras, it can also overload power grids, degrade satellites, and disrupt communications. Extreme events like Carrington have demonstrated the disruptive power of these ejections. Modeling the trajectory and rotation of a CME remains a challenge. The cloud can deform, expand asymmetrically, or be deflected by regions of intense field strength. This variability complicates prediction of its magnetic orientation upon arrival at Earth. Missions like Parker Solar Probe and Solar Orbiter are helping to understand how CMEs form and evolve near the Sun. By measuring the magnetic field and density in the inner regions of the heliosphere, they refine prediction and risk models. CMEs don't occur in isolation. During periods of solar maximum, multiple ejections can occur per week or even per day. In these cases, one CME can pave the way for others, amplifying their effects or altering their propagation. Although most of a CME's mass escapes the Sun, some may recirculate, falling back as coronal rain. This return provides information about the geometry of the ejection and the forces acting during the process. CMEs also serve as a bridge between the Sun and the interstellar medium. They carry magnetism, matter, and angular momentum, shaping the heliosphere and even affecting the environments of other stars. They are exports of solar weather into deep space. In energy terms, a CME can release the equivalent of billions of nuclear bombs. And yet this process occurs regularly on our star, unseen by the naked eye. It's a reminder of the scale at which the Sun operates. Carrington, 1859, the benchmark of chaos. In September 1859, the Sun unleashed a flare so intense that it remains the reference point for all extreme space weather events. Known as the Carrington event, it was observed by Richard Carrington, who saw a sudden brightening on the solar disk during his routine sunspot monitoring. Hours later, Earth felt the impact. The flare was accompanied by a massive coronal mass ejection, CME, that traveled from Sun to Earth in just 17.6 hours, a record speed, indicating an incredibly powerful eruption. Upon arrival, it compressed Earth's magnetosphere and induced electric currents in the ground, creating geomagnetic chaos. The auroras that followed were seen as far south as the Caribbean. In regions like Havana and Rome, skies glowed red and green, startling people unaccustomed to such displays. Some thought the sky was on fire. Miners in Colorado reportedly prepared breakfast thinking it was morning light. Telegraph systems around the world malfunctioned. Operators received shocks, equipment sparked spontaneously, and some systems even continued working after being disconnected from power. Wires acted like antennas, absorbing geomagnetically induced currents that overwhelmed the primitive infrastructure. Despite the 19th century technology, the event left a mark. The disruption of telegraphs, then the backbone of global communication, was a stark demonstration of solar power. Today, the same event could paralyze electrical grids, satellite networks, aviation, and digital infrastructure. Estimates suggest that a Carrington-class event today would cause trillions in damages. Power transformers, especially in high-latitude regions, are particularly vulnerable to geomagnetically induced currents. Blackouts could last weeks or longer, and recovery would be complex and expensive. The event also produced a strong ground-level enhancement, or GLE, in cosmic rays. This rare phenomenon increases radiation doses at flight altitudes and can affect biological tissue, electronics, and radiation-sensitive instruments. GLEs are among the most dangerous aspects of solar storms. Tree ring and ice core data confirmed that Carrington was not unique, but it was certainly extreme. Other events of comparable or greater strength may have occurred in the past, such as the Miyake events. But Carrington remains the clearest case with direct human observations. Carrington's own drawing of the flare and sunspots is still studied today. His meticulous records combined with magnetic observatory logs from around the world allow scientists to reconstruct the storm in detail. It was a case study ahead of its time. The 1859 storm accelerated scientific interest in solar-terrestrial connections. It marked a turning point in space weather awareness, even if the concept itself was not yet formalized. Carrington unknowingly documented the birth of heliophysics. The event also prompted early speculation about solar flares affecting Earth. While the mechanisms remained unclear, the temporal link between solar activity and geomagnetic disturbance was undeniable. This insight laid the groundwork for future research into solar impacts on technology. Models now use Carrington-like scenarios as upper bounds for preparedness. Simulations incorporate CME speed, density, and magnetic orientation to estimate worst-case outcomes. Governments and space agencies use these to plan contingencies for infrastructure resilience. Modern satellites monitor the sun continuously, and early warning systems can provide hours of lead time. But predicting the magnetic orientation of a CME, the detail that determines severity, remains an unsolved challenge. Carrington would still catch us off guard. The event's importance lies not only in its intensity, but in its completeness. It involved a flare, CME, fast transit, visible auroras, technological impact, and long-term archival data. It's the full spectrum of solar-terrestrial interaction, all in one package. Quebec, 1989. 6 million in the dark. On March 13, 1989, a powerful geomagnetic storm plunged the entire province of Quebec, Canada, into darkness. Within 90 seconds, a cascading failure in the Hydro-Quebec power grid left over 6 million people without electricity. It was a modern taste of solar disruption. The storm was triggered by a CME that erupted from the sun days earlier. As the shock wave reached Earth, it compressed the magnetosphere and drove powerful electric currents into the ground, especially in regions with conductive bedrock like Quebec. This induced voltage in the power infrastructure. Transformers in the network absorbed massive geomagnetically induced currents, GICs. Protective systems failed to respond quickly enough. A key transformer in the James Bay network tripped, setting off a chain reaction that destabilized the entire grid. The blackout lasted for 9 hours. The event occurred just before dawn. Subway systems halted, businesses shut down, and communication lines were interrupted. In the absence of power, public services were strained, and Quebec's winter conditions added to the discomfort and logistical challenges. Outside of Canada, satellites and power systems in the United States also recorded anomalies. Transformers in New Jersey and New England experienced overheating. Some satellites drifted out of position, and radio communication in high frequencies became unreliable for hours. The storm also produced auroras visible as far south as Texas and Florida, a striking visual indicator of the intensity. These auroras were caused by solar particles funneling along magnetic field lines into Earth's upper atmosphere, exciting oxygen and nitrogen atoms. Quebec 1989 was not as powerful as the Carrington event, but its impact on a modern power grid was a wake-up call. It demonstrated that even moderate solar storms could induce widespread technological disruption when conditions align unfavorably. Following the event, the power industry took geomagnetic risk more seriously. Utilities began to monitor space weather forecasts, install GIC blocking systems, and develop response protocols. Quebec's blackout helped catalyze an entire field of operational space weather readiness. The event also highlighted the vulnerability of high-latitude regions. Earth's magnetic field lines converge near the poles, creating paths for solar particles and currents to reach the surface more easily. Northern grids, therefore, remain at higher risk. Insurance and risk assessment agencies now include solar storms in their calculations. Quebec 1989 showed that the sun's influence isn't limited to satellites. It can hit terrestrial systems hard. Infrastructure connected to long transmission lines is especially exposed. Space agencies like NOAA and ESA expanded their monitoring capabilities after the blackout. Satellites such as SOHO and ACE were tasked with providing real-time solar wind and magnetic field data, giving operators a chance to prepare for incoming storms. The Quebec event also contributed to public understanding of solar risks. News coverage of auroras and blackouts introduced many to the concept of space weather, turning what was once a niche concern into a mainstream topic with practical consequences. From a scientific perspective, the blackout provided valuable data. Ground magnetometers, transformer logs, and satellite telemetry all helped model how GICs flow through power grids. These models continue to evolve, improving forecasting and protective strategies. The blackout underscored that we are increasingly dependent on systems vulnerable to the sun. GPS, aviation, internet cables, and pipelines can all be affected. Quebec 1989 was not just a local failure, it was a signal of global vulnerability. Polar flights and radiation. Commercial air travel through Earth's polar regions presents a unique vulnerability to solar activity. Unlike equatorial routes, polar flights pass under open magnetic field lines, where energetic particles from solar storms can enter the atmosphere more directly. This exposes aircraft, crews, and passengers to increased radiation risk during space weather events. Under normal conditions, cosmic radiation at cruising altitudes is already higher than at sea level. During solar proton events, the dose can spike significantly, especially over the poles. Airline operators, therefore, monitor space weather to adjust flight paths or altitudes when radiation levels are forecast to rise. The FAA and other aviation authorities have established dose thresholds to limit exposure. Pregnant crew members and frequent flyers are particularly considered in these calculations. While a single polar flight during a storm doesn't pose acute danger, cumulative exposure matters over time. Beyond radiation, polar regions are also vulnerable to radio blackouts. High-frequency HF communication, vital for polar operations, relies on the ionosphere. Solar flares and geomagnetic storms can disrupt or completely disable these frequencies, forcing rerouting of flights to maintain contact. These communication blackouts are more than inconveniences, they pose safety risks. When pilots lose real-time communication with ground control, coordination of air traffic becomes more complex. For this reason, solar activity forecasts are integrated into aviation planning. Several events in the past have prompted diversions. For instance, during the 2003 Halloween storms, multiple airlines rerouted polar flights to lower latitudes. While costly, these measures prevented unnecessary radiation exposure and ensured continuous communications. Airlines today use real-time data from NOAA, NASA, and the International Space Environment Service to track solar conditions. If a major event is predicted or detected, operations teams decide whether to reroute, cancel, or delay polar routes based on predefined protocols. Flight altitudes also influence exposure. At higher altitudes, the shielding effect of Earth's atmosphere diminishes. Descending a few thousand feet can reduce radiation dose, a tactic sometimes used when rerouting is not feasible. The South Pole is particularly exposed due to weaker geomagnetic shielding in that region. Flights over Antarctica or near the southern auroral oval must account for both communication and radiation concerns, especially during solar maximum phases. Polar routes are attractive for their fuel efficiency and reduced travel time between continents. However, as solar cycle activity fluctuates, so does the operational risk. Airlines must balance efficiency with passenger and crew safety, adapting to changing space weather conditions. The development of radiation models like NIARIS and CARI helps estimate in-flight exposure based on solar conditions, altitude, and latitude. These models support aviation decision-making and regulatory compliance by forecasting potential dose rates for various routes. Astronomical observatories and research stations in polar regions also face space weather challenges. Though stationary, their reliance on satellite links and electrical systems mirrors that of aircraft. Severe storms can disrupt scientific missions or delay logistics operations. As commercial spaceflight and high-altitude tourism expand, the intersection between aviation and space weather becomes more pronounced. Stratospheric balloon flights and suborbital trips may face radiation levels closer to those encountered in low Earth orbit. Ultimately, polar aviation exemplifies how solar physics intersects with everyday systems. What begins as a flare on the sun can ripple into airline decisions, flight paths, and passenger itineraries. It's space weather not in theory, but in practice across our skies. As monitoring improves and predictive models advance, polar flights will remain viable but better safeguarded. Awareness, preparation, and flexibility are the tools that keep aviation resilient under the sun's unpredictable influence. Astronauts and shielding. In space, Earth's protective magnetic field no longer shields astronauts from solar particles and cosmic rays. This makes radiation one of the most serious hazards for crewed missions beyond low Earth orbit. Shielding strategies are essential and often define mission design and safety protocols. During solar storms, the flux of high-energy protons can increase dramatically. Without adequate protection, astronauts could receive doses high enough to cause acute radiation sickness or long-term health effects. The challenge is to provide shielding without adding excessive mass to the spacecraft. On the International Space Station, ISS, shielding is carefully distributed. Modules are designed with layers of aluminum and polyethylene to reduce particle penetration. During solar events, crews move to the most protected areas, typically in the service module or near water supplies, which offer additional radiation buffering. Radiation exposure is cumulative. Each mission adds to an astronaut's career dose, which is tracked and regulated. Space agencies set limits based on age, sex, and mission role, aiming to minimize lifetime cancer risk and other potential outcomes. The galactic cosmic rays, GCRs, pose a constant background threat, even outside solar events. Unlike solar protons, GCRs are harder to shield due to their extremely high energy. Materials that stop them often generate secondary particles, complicating the shielding problem. Water, polyethylene, and hydrogen-rich compounds are favored for their ability to block protons without excessive secondary production. Some future spacecraft may use tanks of water or fuel as part of the shielding system, integrating structure and safety. On the lunar missions, the lack of a magnetosphere and thin regolith present new challenges. Astronauts on the Moon have minimal protection and must rely on quick shelter access during solar particle events. Forecasting becomes critical, as does emergency shelter design. Mars missions face even greater difficulties. Transit to and from the planet and surface stay expose crews to extended radiation levels. Some proposals involve building habitats with Martian soil or using underground lava tubes to shield long-term explorers. One extreme solution under consideration is active shielding, creating artificial magnetic fields around spacecraft. While still theoretical, such systems could deflect charged particles, mimicking Earth's magnetosphere, but power and stability requirements remain major obstacles. NASA and ESA test shielding materials on the ISS through passive dosimeters and instrumented mannequins like Matryoshka. These experiments measure how radiation varies by location and how different materials attenuate it. Each data set informs future mission design. Private companies entering human spaceflight must also consider radiation in spacecraft architecture. Whether for orbital hotels or moon bases, shielding decisions affect cost, weight, and risk, making them central to engineering and operational planning. Crew protocols include not just physical shielding, but mission timing. Flights are often scheduled to avoid solar maximum, when flare and CME activity is higher. Medical monitoring pre, during, and post-mission also ensures early detection of any health impacts. Artificial intelligence may aid future radiation response. Onboard systems could monitor solar conditions and recommend shelter-in-place strategies in real time. Automation ensures fast reaction when ground contact is limited or delayed. Radiation remains one of the greatest barriers to long-term human space exploration. While microgravity, isolation, and logistics challenge the body and mind, radiation silently threatens tissue, DNA, and organs, demanding constant innovation in protection. As we move toward moon bases and Mars journeys, shielding will shape what's possible. It's not only a matter of walls and thickness, but of materials, monitoring, and mission architecture. In space, the sun is beautiful and dangerous. Shielding makes the difference. A kill zone in solar system center. In solar observation, there's a critical region that draws special attention, the apparent center of the solar disk. When an active region is positioned precisely at this point, it aligns with the Sun-Earth line, meaning it's from there that the most dangerous ejections have the greatest chance of hitting us directly. This is what many informally call the fire zone. The geometry of the alignment is crucial. When a CME is released from this position, its propagation vector aligns with the interplanetary field connecting the Sun to Earth. This increases the probability of a frontal impact, and with it, the chance of severe storms in the near-Earth environment. Active regions that reach the center of the disk are generally monitored more closely by space agencies. If they exhibit twisted fields, flux ropes, or complex spot patterns, the risk of significant flares and CMEs increases. This is the phase of greatest surveillance in the solar rotation cycle. This zone is so strategic that some risk models consider the central position as the point of greatest potential danger. This is due not only to the direction of the ejection, but also to the ability of instruments, such as coronagraphs, to better detect the symmetry of the expanding cloud. During extreme events, such as the Carrington flare or the Halloween flares of 2003, active regions were close to or intersecting this zone. This coincidence reinforces the importance of understanding how solar positioning influences spatial geodynamics. Besides alignment, another relevant factor is the inclination of the ejection. Even if it occurs at the center, a CME can be launched at an angle, deviating from the direct line. Therefore, observing the magnetic topology of the active region is essential to estimate the cloud's likely orientation. The central zone also serves as a privileged window for spectroscopic measurements. With less geometric distortion, it is possible to analyze ultraviolet and X-ray emissions more accurately, helping to predict the thermal and dynamic behavior of the approaching region. Images of sunspots seen from this point reveal their true outlines, without the projection effects that distort regions near the edge. This allows for accurate mapping of their extent, field, and evolution, critical information for activity forecasting. During the passage through this region, peak emission is expected in several spectral bands, as the observation angle favors the detection of symmetrical brightnesses. Photometry also becomes more reliable, increasing the accuracy of solar models. There is a time window of approximately 3 days during which an active region remains in the kill zone. During this period, any flare or CME becomes more relevant to early warning systems as the response time for ground preparation is short. Probes positioned at L1, such as Discover, continuously monitor the solar wind coming from that direction. When a central region releases an ejection, magnetic field, density, and velocity data help more accurately calculate the expected impact. Side-observing satellites, such as those on the stereo mission, complement these analyses with a perspective view. They allow us to confirm whether an ejection that appears central is also symmetrical or has a trajectory deviation that would reduce the risk. The central zone also serves as the basis for three-dimensional simulations of CME propagation. Using data from magnetograms, helioseismology, and extreme emissions, models like ENLIL project the cloud's path and its interaction with the interplanetary field in real time. Granulation, the sun's bubbling floor. The solar photosphere, which we see as the star's surface, is far from static. When viewed at high resolution, it reveals a mosaic pattern formed by dynamic plasma cells, solar granulations. Each cell is the size of Texas and lasts only a few minutes. This bubbling pattern is the result of convection. Columns of hot plasma rise from within the sun and, upon reaching the photosphere, cool, losing energy to space. The plasma then sinks down the edges of the cells, initiating a new convective cycle. The bright cells correspond to the rising plasma, hot and less dense. The darker edges indicate the cooled material sinking. This constant movement renews the sun's visible surface at every instant, creating a continuous boiling effect. Granulation is a direct manifestation of energy transport from the convective zone to the surface. While in the radiative zone, heat travels slowly through re-emission. In the photosphere, it emerges in vertical jets that travel tens of thousands of kilometers in a matter of days. Observations with ground-based and orbital telescopes allow us to record these cells in stunning detail. The images show how the structure changes in seconds, highlighting the turbulent and chaotic nature of the solar surface. The plasma velocity in the cells can reach 2 kilometers per second. This dynamic generates acoustic waves that reverberate throughout the solar interior and are used in helioseismology to map the star's inner layers. Each cell is a miniature sound source. In addition to normal granulations, there are supergranulations, larger patterns approximately 30,000 kilometers across with lifetimes of up to 2 days. These structures modulate the distribution of magnetic fields and influence the formation of active regions. Studying granulation helps us understand how the magnetic field is organized on the surface. Convective flows drag the field lines, concentrating them in specific regions and facilitating the emergence of magnetic spots and arcs. Three-dimensional magnetoconvection models simulate granulation based on fluid physics, thermal transport, and magnetic interaction. These models explain the visual texture of the photosphere and help predict how the solar field reorganizes. At certain times, fluctuations in granulation indicate deeper instabilities. Regions with anomalous patterns may precede the emergence of sunspots or be associated with large-scale updrafts, such as those that feed active regions. Although it may seem like an aesthetic detail, granulation is an essential component of solar function. It represents the endpoint of an energy pathway that began in the core and took hundreds of thousands of years to emerge. Each granule cell is a testament to the balance between gravity, thermal pressure, and magnetism. Its shape and duration depend on fundamental properties of the solar plasma, such as viscosity, conductivity, and field strength. Instruments like the Solar Optical Telescope, SOT, aboard Hinode, and DKIST in Hawaii provide ultra-high-resolution data for studying these structures. Their images show how the structure changes in seconds, highlighting the turbulent and chaotic nature of the solar surface. Granulation also interacts with larger phenomena, such as shock waves from flares and the passage of magneto-acoustic waves. It is not just a surface pattern, but part of the network that connects all layers of the solar atmosphere. Solar dynamo, the engine of chaos. The sun's magnetic field is neither fixed nor static. It arises from the interaction between the motions of the plasma within the star and its conductive properties, a process known as the solar dynamo. This invisible machine is the heart of the magnetic activity cycle we observe on the surface. The dynamo's base lies in the convective zone, where columns of boiling plasma continually rise and fall. As they move, these masses carry magnetic field lines with them, stretching and twisting the flows like elastic threads within a conductive liquid. This movement is not uniform. The Sun's rotation varies with latitude and depth, creating shear zones. The main shear zone occurs in the tachocline, a thin layer between the radiative zone and the convective zone, where the velocity gradient is maximum. At the tachocline, the magnetic field is amplified and reorganized into ordered structures. It is there that the global dipolar field transforms into more complex toroidal fields, which later emerge as sunspots and magnetic arcs. The surface chaos originates from this deep engine. Every approximately 11-year cycle, the Sun's global magnetic field reverses. This phenomenon is a direct product of dynamo action. A growing toroidal field distorts the original field until it cancels itself out and is reborn inverted. The energy doesn't disappear, it changes form. During solar maximum, the magnetic field reaches its peak complexity. Field lines emerge strongly at various latitudes, creating sunspots, flares, and CMEs. This is the moment of greatest visible dynamo activity. During solar minimum, activity diminishes, but the dynamo doesn't stop. Reorganization continues within, preparing for the next reversal. This cycle between order and chaos, between structure and chaos, is a fundamental signature of the Sun's magnetic functioning. Three-dimensional magnetohydrodynamic simulations help understand how convective flows, rotation, and shear create this dynamic field. These models reproduce the formation of active bands, solar cycles, and even variations in prolonged minima. Small changes in the tachocline depth or convection intensity can have large effects on the cycle. Therefore, understanding the dynamo is crucial for predicting future solar activity and the risks associated with space weather. Despite decades of study, the solar dynamo still presents mysteries. It's unclear, for example, why weaker cycles or prolonged minimums occur so seemingly irregularly. The system's sensitivity challenges current models. Some theories propose that nonlinear feedbacks between the magnetic field and convection can cause cyclical or chaotic variations. Other studies investigate the role of meridional currents, flows that transport the magnetic field from the surface to the poles and vice versa. The solar dynamo is an exemplary example of a complex system, sensitive to disturbances, with multiple feedback loops, and capable of generating regular patterns and unexpected surges. Understanding it requires fluid physics, chaos theory, and advanced computer simulations. This mechanism isn't unique to the Sun. Other bodies with convection and rotation also generate magnetic fields, from planets like Jupiter to red dwarf stars. But the solar dynamo is the best documented and studied to date. The relative stability of solar irradiance depends in part on the balance of the dynamo. When this motor enters more stable phases, the dipolar field takes over. When it destabilizes, surges and rapid variations occur, such as large minimums and maximums.
Differential rotation, 25 days at the equator, 35 at the poles. Unlike a solid body, the Sun rotates like a fluid. This means that different parts of its surface complete a rotation in different times. At the equator, the rotation takes about 25 days. At the poles, this time can reach 35 days.
a difference that has profound effects. This differential rotation is a direct consequence of the Sun's internal structure. The star is composed of plasma, not rock or metal. The plasma's motion is influenced by pressure gradients, magnetic fields, and Coriolis forces, creating complex rotational dynamics. The equator, because it receives greater angular momentum and has greater mass mobility, rotates more rapidly. At mid-latitudes, the velocity gradually decreases until it reaches the poles. This asymmetric distribution is precisely observed through Doppler spectroscopy. Helioseismology also confirms this variation. By analyzing the acoustic waves that travel through the solar interior, it is possible to reconstruct the rotation profile at different depths and latitudes. These measurements reveal that the differential rotation extends into the convective zone. This difference in speed is the driving force behind the solar dynamo. The shear generated between layers rotating at different speeds twists the magnetic field lines, amplifying them. The toroidal field, the basis of solar activity, arises from this uneven motion. The transition region between the solid rotation of the radiative zone and the fluid rotation of the convective zone is called the tachocline. This thin layer is where shear is maximum and where the magnetic field is believed to be organized into coherent structures. Differential rotation also explains observational patterns, such as the migration of sunspots throughout the cycle. They emerge at mid-latitudes and, over time, move closer to the equator. The famous butterfly diagram is a direct consequence of this phenomenon. During the solar cycle, the interaction between rotation and convection can alter the pattern of sunspot appearance. In certain cycles, the latitudinal shift is faster or more asymmetric, indicating variations in the rotation profile and magnetic field strength. The effect of differential rotation is not limited to the surface. At greater depths, especially at the base of the convective zone, the rotation profile can be more uniform. Understanding how this transition occurs is one of the challenges of solar modeling. Numerical simulations of global convection show that subtle changes in rotation can trigger reorganizations of the magnetic field. Rotation is therefore not only a consequence of solar structure, but also a force that feeds back into the field's behavior. Continuous observation of solar rotation is carried out by instruments such as the Helioseismic and Magnetic Imager, HMI, on the SDO satellite. This data helps predict the emergence of active regions and contributes to monitoring the solar cycle. Differential rotation is common in convective stars. In other sun-like stars, this uneven rotation also fuels cycles of magnetic activity. Comparing these cycles helps us understand whether solar behavior is typical or an exception. During grand minimums, such as the Maunder, the differential rotation pattern can change. The absence of spots and the long lull suggests that the internal engine slows down or reorganizes its dynamics, a hypothesis still under investigation. Farside in 3D, stereo and global mapping. For centuries, the far side of the Sun remained a blind spot. As the Sun rotates roughly every 27 days, only one hemisphere is visible from Earth at a time. For solar forecasting, this left a significant gap. Regions of magnetic activity could emerge unseen, only to rotate into Earth's view with little warning. This limitation changed with the launch of NASA's STEREO mission in 2006. Two nearly identical spacecraft were placed in solar orbits ahead of and behind Earth. As they drifted apart over time, they captured stereoscopic images, enabling the first 3D mapping of the entire solar surface. By combining observations from Stereo A and Stereo B with Earth-based data, scientists constructed near-complete solar maps. For the first time, space weather forecasters could monitor active regions on the far side and anticipate their potential effects before they turned Earth-facing. These global views improved solar modeling significantly. When a large sunspot or magnetic region rotates into view, forecasters now often have days of prior observation from the far side. This enables better CME risk assessments and satellite protection planning. Stereo's instruments included EUV imagers, coronagraphs, and heliospheric imagers. Together, they provided a complete picture from solar surface to interplanetary space. The spacecraft could detect flares, CMEs, and their evolution with unique angular perspectives. The mission also helped validate the techniques of helioseismology, which had been used to infer activity on the far side through acoustic oscillations. Stereo's direct views confirmed many far-side detections and refined seismic models. During its peak phase, the Stereo constellation gave nearly 360 degrees solar coverage. Even when Earth couldn't see the far hemisphere, the two spacecraft could stitch the missing pieces together. This was especially critical during solar maximum, when active regions abound. Stereo B was lost in 2014, breaking the full 3D coverage. However, Stereo A continued to operate, providing one flank of the Sun's view. In 2023, it briefly returned to Earth's vicinity, allowing calibration of its instruments against newer missions like Solar Orbiter. Future missions aim to restore full far-side monitoring. A spacecraft at the Earth-Sun L5 point would have a constant side view of the Sun, bridging the observational gap. This configuration could ensure permanent early warning for space weather events. Global solar mapping is not just academic. It underpins forecasting models like WSA-Enlil, which simulate solar wind and CME propagation. Knowing what lies around the Sun improves accuracy in predicting geomagnetic storms that affect Earth's systems. Monitoring the far side is also crucial for understanding the Sun's magnetic cycle. Active regions on the far side contribute to the overall magnetic flux and influence the evolution of the solar dynamo. Without that data, models remain incomplete. Instruments like GONG and SOHO complement space-based views with Earth-based helioseismic data. Together they form a hybrid observation network that maximizes coverage even when spacecraft availability is limited. As solar activity becomes more intense in approaching cycle peaks, far-side awareness becomes a frontline defense. Power grids, communication systems, and astronauts benefit from the added lead time that global mapping provides. SDO, Sun in Ultra Resolution and Multicolor. Launched in 2010, NASA's Solar Dynamics Observatory, SDO, revolutionized our view of the Sun. Unlike previous missions limited to a few wavelengths or low temporal resolution, SDO offers full-disk imagery in multiple ultraviolet bands with extraordinary detail and cadence. The Atmospheric Imaging Assembly, AIA, aboard SDO, captures images in 10 different UV and extreme UV channels. Each channel corresponds to plasma at specific temperatures, revealing different layers of the solar atmosphere, from the chromosphere to the corona. This multicolor approach allows scientists to observe how solar features behave at different energies. A single solar flare, for instance, might look entirely different at 171 angstroms than at 335 angstroms. Each wavelength uncovers a piece of the energetic puzzle. The detail is staggering. SDO captures one image every 12 seconds, producing over a terabyte of data daily. Features as small as a few hundred kilometers can be resolved, fine enough to track dynamics within coronal loops or granulation patterns on the photosphere. The helioseismic and magnetic imager, HMI, another instrument on board, measures the magnetic field across the solar disk and records Doppler shifts in surface oscillations. These datasets help track sunspot evolution and support helioseismic studies. With these combined instruments, SDO offers an unparalleled toolkit to study solar variability. Researchers can correlate magnetic changes with ultraviolet flares, follow filament eruptions from chromosphere to corona, and trace CME origins frame by frame. The mission has contributed immensely to space weather research. By offering real-time data and high-resolution views of flare development, SDO enhances our ability to forecast when and where solar storms will originate. SDO imagery is also widely used for public outreach and education. Its stunning color composites and time-lapse videos of solar activity have made the sun visible and dynamic to audiences around the world, a tool for both science and wonder. From a scientific standpoint, the ability to monitor temperature-specific layers simultaneously is transformative. It enables time-resolved studies of energy transfer and plasma flows, critical to understanding coronal heating and flare mechanisms. SDO data feeds directly into models of solar irradiance, the energy received from the sun at various wavelengths. These models help quantify how solar variability affects Earth's upper atmosphere, climate systems, and satellite orbits. The mission has also contributed to solar cycle analysis. By tracking how active regions emerge, migrate, and decay across cycles, SDO helps refine our understanding of the solar dynamo and its rhythmic behavior. Despite its rich data output, SDO has maintained consistent calibration and stability. This makes its decade-long archive invaluable for longitudinal studies of solar phenomena, from flare rates to granulation patterns and magnetic flux evolution. SDO's long baseline of uninterrupted data ensures continuity with upcoming missions like Solar Orbiter and DKIST. These future observatories will benefit from SDO's foundational datasets for comparison and calibration. The success of SDO sets a new standard for solar observation. Its combination of breadth, depth, and resolution redefined what it means to watch the sun, turning a static star into a dynamic, living laboratory. SOHO and coronagraphs, artificial eclipses. The outer atmosphere of the sun, the corona, is normally invisible to the naked eye. Its faint glow is overwhelmed by the sun's brilliance except during total solar eclipses. But relying on such rare alignments was limiting. Scientists needed a way to observe the corona continuously. Enter SOHO, the Solar and Heliospheric Observatory. Launched in 1995, SOHO transformed solar observation with a suite of instruments, including its iconic coronagraphs. These devices simulate eclipses by blocking the bright solar disk with an artificial occulting disk. By imitating an eclipse, SOHO's coronagraphs allow the faint coronal structures to appear clearly. Massive loops, streamers, and plasma outflows become visible in real time. This capability is key to tracking CMEs, vast clouds of solar material ejected into space. SOHO's LASCO, or Large Angle and Spectrometric Coronagraph, is divided into multiple channels, each capturing different scales and brightness levels of the corona. This tiered approach offers a complete picture of coronal dynamics, from small outbursts to global reorganizations. One of LASCO's most dramatic features is the halo CME. When a CME appears as a circular expansion surrounding the occulting disk, it indicates a launch directed either directly at or away from Earth. These events demand close attention from space weather forecasters. SOHO has documented thousands of CMEs, revealing their speeds, structures, and directions. It's helped categorize CMEs by morphology and velocity, crucial for predicting whether they'll cause geomagnetic storms or pass harmlessly through space. Before SOHO, CME detection was sparse and largely unstructured. The coronagraph changed that. Now every significant ejection is recorded, measured, and modeled. SOHO effectively made the invisible corona a continuous part of scientific observation. Coronagraphy also uncovered dynamic features like coronal waves and streamer blowouts. These phenomena, linked to magnetic reconfigurations, show how interconnected the corona is with the Sun's interior and surface activity. SOHO's long-term presence gives us the ability to compare CME behavior across solar cycles. It's revealed how the frequency and characteristics of ejections change over time, tying directly into our understanding of the solar magnetic cycle. The observatory also contributed to heliospheric imaging, allowing indirect tracking of solar wind and CME evolution beyond the coronagraph's field. Paired with instruments from other missions, it supports full propagation modeling to Earth and beyond. SOHO's role extends to planetary defense. Its data are used to forecast space weather impacts on satellites, astronauts, and power systems. By offering several hours to days of warning, it serves as a key layer in our technological shield. SOHO also inspired coronagraph designs for other missions, including Stereo and Solar Orbiter. These next-generation instruments benefit from lessons learned during SOHO's decades of operation, especially in image calibration and background subtraction. The longevity of SOHO, far exceeding its original mission timeline, is a testament to its engineering and importance. Even as newer missions come online, SOHO remains a reliable workhorse for CME monitoring and coronal studies. The perfect watch point between Sun and Earth. The Lagrange point 1, L1, sits approximately 1.5 million kilometers from Earth in the direction of the Sun. At this position, the gravitational forces of the Earth and Sun balance with the orbital motion of a spacecraft, allowing it to remain fixed relative to the two bodies. This unique vantage point offers an uninterrupted view of the Sun. Unlike Earth-bound observatories, an instrument at L1 can monitor solar activity continuously without interference from the planet's shadow or atmospheric distortion. L1 is a frontline post for space weather monitoring. When a CME erupts from the Sun, it typically reaches L1 about 30 to 60 minutes before impacting Earth. Instruments stationed there measure its magnetic field, density, velocity, and orientation in real time. The ACE and DS-COVR spacecraft currently occupy L1. Their instruments provide essential data for early warning systems. By analyzing magnetic polarity and southward field components, forecasters estimate whether an incoming CME is likely to trigger a geomagnetic storm. The ability to monitor solar wind at L1 has revolutionized response capabilities. Space agencies can issue alerts for satellites, power grids, and communication systems, potentially mitigating damage from solar events. L1 also hosts solar observatories. SOHO, for instance, resides at this point, taking advantage of the stable line of sight for coronography and helioseismology. The consistent geometry supports long-term studies and simplifies instrument calibration. Future missions are likely to continue populating L1. Its strategic role in planetary defense and solar science makes it a prime location for space-based weather observatories and deep space communication relays. Data from L1 enable real-time modeling of the heliospheric environment. By feeding CME observations into propagation models, researchers forecast arrival times and intensities with increasing accuracy, especially during solar maximum. The position also allows spacecraft to see Earth and Sun simultaneously. This is valuable for missions studying Earth's response to solar activity, such as ionospheric disturbances, auroras, or thermospheric expansion. L1 is part of a broader Lagrange system, including L2, used by James Webb, and proposed L4, L5 space weather monitors. Together, these points offer geometric diversity for 360-degree solar coverage and deeper insight into the Sun-Earth connection. In an age of increasing technological dependence, L1 has become a sentinel. Its data feed directly into NOOA's alerts, satellite operations, and infrastructure management, often with just minutes to act. The concept of using Lagrange points for observation dates decades, but its implementation at L1 proved transformative. It gave scientists and engineers a stable, solar-facing eye on our star and a buffer zone to prepare for its outbursts. Though remote, L1 is now a hub of solar observation and forecasting. The information gathered there travels quickly across the globe, influencing everything from satellite shielding to airline routes and power grid readiness. It's also a reference for space mission design. Missions venturing toward Mars or deeper space may use L1 orbits for gravity assists, communication relay, or staging, further embedding its role in space operations. As solar cycles wax and wane and our reliance on satellites grows, L1 remains a critical node. It's not just a watch point, it's Earth's early warning system, where physics, engineering, and foresight meet. Solar orbiter and the solar poles. The Sun's poles have long been among the most mysterious regions of our star. From Earth's ecliptic vantage point, we see the Sun nearly edge-on, making direct observation of its polar regions almost impossible. Yet these areas may hold critical clues to the solar magnetic cycle. To address this, ESA and NASA launched the Solar Orbiter mission in 2020. Unlike previous spacecraft, Solar Orbiter's trajectory gradually tilts above the Sun's equator, enabling unprecedented views of the polar regions, a first in solar science. The spacecraft carries a suite of 10 instruments, combining remote sensing with in-situ measurements. It observes the Sun in multiple wavelengths while directly sampling the solar wind and magnetic fields in its environment. This dual capability sets it apart from most missions. One key goal is to understand how the solar dynamo functions near the poles. Current models suggest the polar magnetic fields play a pivotal role in resetting the Sun's global field during each 11-year cycle. But these models lacked direct polar observations until now. High-latitude views also help clarify how magnetic flux is transported across the Sun's surface. The meridional circulation, a slow flow from equator to pole, appears to vary across cycles, and these variations may explain irregularities in solar activity. Solar Orbiter has already returned striking images of the poles, showing complex magnetic structures, bright spots, and patterns that differ from equatorial regions. These differences may reveal distinct magnetic behavior in the high-latitude zones. By analyzing magnetic polarity at the poles, Solar Orbiter will refine our understanding of the Sun's field reversals. These reversals mark the end of each solar cycle and are key predictors of future solar maximum strength. The mission's observations support improved space weather forecasting. Polar magnetic fields help seed the heliospheric current sheet, which governs solar wind structure and CME propagation. Knowing their behavior enhances prediction models. Solar Orbiter also provides context for in situ measurements from spacecraft like Parker Solar Probe. Together, they offer a multi-dimensional view of the Sun's magnetic engine, from deep within the corona to the far reaches of interplanetary space. The spacecraft's heat shield and articulated instruments allow it to operate closer to the Sun than any European mission before. It balances proximity with angled views to reveal both the fine detail and large-scale dynamics of solar activity. Its elliptical orbit brings it as close as 0.28 AU from the Sun, inside Mercury's orbit. Over time, gravitational assists from Venus increase the inclination of the orbit, gradually lifting its observational angle above the poles. These unique measurements inform dynamo models across stellar types. By understanding how our star generates and reorganizes its magnetic field, we gain insight into other stars with different mass, rotation, and convection profiles. Solar Orbiter also observes solar flares, prominences, and CMEs with high resolution. By linking these events to their origins, especially at high latitudes, the mission helps trace the birth of solar storms more accurately. In conjunction with Earth-based and L1 observatories, Solar Orbiter expands our spatial coverage. Its shifting viewpoint allows triangulation of flares and CMEs, and its polar views offer a missing piece in full Sun magnetic field reconstructions. As the mission continues, its high-latitude vantage will become increasingly valuable. By peering into the Sun's crown, Solar Orbiter helps us understand the rules behind the cycle, and perhaps why those rules sometimes break.
Sunrise, stratospheric balloon. Observing the Sun from Earth is limited by the atmosphere. Even at high altitudes, air absorbs much of the ultraviolet and extreme ultraviolet light crucial for solar studies. Space telescopes solve this, but they're expensive. A high-flying alternative: the Sunrise Balloon Observatory. Sunrise is a balloon-borne solar telescope launched to the stratosphere, over 35 kilometers above Earth's surface, where 99% of the atmosphere is below. At this height, ultraviolet light can be captured with clarity approaching space-based instruments. Unlike satellites, Sunrise is a temporary mission. It flies on long-duration balloons that drift across polar regions during summer, where constant daylight allows uninterrupted solar observation for days at a time. It's a unique blend of mobility and high-resolution imaging. The telescope has a 1-meter primary mirror, making it one of the largest solar telescopes ever flown above Earth. Its resolving power allows it to detect solar features down to about 50 kilometers in size, finer than most space-based UV imagers. Sunrise focuses on the photosphere and chromosphere, especially small-scale magnetic elements. It investigates how these elements interact, coalesce, or disperse, helping researchers understand the magnetic roots of solar activity. During its missions, Sunrise has captured detailed views of granulation patterns, magnetic flux tubes, and dark cores of sunspots. These structures reflect the convective and magnetic behavior that drives larger phenomena like flares and CMEs. Its ultraviolet imaging is particularly valuable for studying heating processes in the lower atmosphere. By observing regions where magnetic fields emerge and reconnect, Sunrise probes how energy moves from the surface upward. The platform carries several instruments, including a UV filter imager, magnographer, and spectropolarimeter.
These tools capture not just intensity, but vector magnetic fields and Doppler shifts, essential for understanding dynamics. Sunrise's data have helped bridge gaps between numerical models and observed behavior. By providing real-world examples of small-scale magnetic interactions, it validates or refines simulations of solar convection and field evolution. One major advantage of balloon-based observation is cost efficiency. While space missions run into billions, balloon payloads like Sunrise offer high-end science for a fraction of the price, and with modular upgrades between flights. Sunrise has completed multiple successful flights, each lasting about 5 to 6 days. It returns its data after landing, offering vast datasets for months of post-flight analysis. New versions of the payload are planned with enhanced sensitivity. The mission also demonstrates the utility of high-altitude platforms for solar research. These observatories can target niche scientific goals with precision optics and flexible deployment schedules, ideal for testing new technologies. In addition to science, Sunrise supports training of engineers and researchers. Balloon missions serve as test beds for novel designs that may later be adapted for orbital missions, bridging the gap between lab and space. While limited in duration, each Sunrise flight yields high-impact science. Its ability to resolve sub-arc-second features makes it invaluable for exploring the smallest magnetic structures that shape the solar atmosphere. From above the clouds, Sunrise watches the sun's surface with surgical detail. It reminds us that even from the edge of space, we can learn volumes with the right optics, timing, and elevation. Einstein Tower and the history of solar spectroscopy. Standing in the woods of Potsdam, the Einstein Tower is a fusion of science and architecture. Completed in the early 1920s, it was designed by architect Erich Mendelsohn to house a solar observatory dedicated to testing one of the most ambitious ideas of its time, Einstein's general relativity. The tower's main scientific instrument is a solar telescope embedded within its unusual concrete shell. It channels sunlight down through mirrors and lenses to a subterranean laboratory where the spectrum of the sun could be recorded with great precision on glass plates. Solar spectroscopy was already well established by then. Scientists used it to identify elements in the solar atmosphere by analyzing absorption lines in the spectrum. The Einstein Tower aimed to measure tiny shifts in these lines caused by gravitational redshift, predicted by Einstein's theory. Although the telescope's sensitivity fell short of confirming the effect at the time, the tower became a hub of solar physics. It contributed to decades of detailed spectroscopic records, capturing the sun's surface and atmospheric dynamics in extraordinary detail. These records weren't just scientific, they formed a visual diary of the sun. Entire disks imaged daily, showing sunspots, limb darkening, and spectral variations. Each photographic plate holds a moment in the life of our star, frozen in data-rich emulsion. The building itself is an icon of expressionist architecture. Its flowing, organic form mirrors the fluid dynamics it was built to study. Over time, it became as much a symbol of scientific ambition as a tool of observation. Inside, the optical path remains operational. Restoration efforts have preserved the original spectrographs and equipment, allowing the Einstein Tower to continue educational and limited scientific work while serving as a monument to early modern astrophysics. Its contribution to solar physics is enduring. Researchers used its data to study solar rotation, chromospheric activity, and magnetic field signatures. The observatory trained generations of scientists, building expertise in solar instrumentation and analysis. Spectroscopy remains central to solar science. Modern instruments, both ground-based and spaceborne, still rely on the principles honed in places like the Einstein Tower, measuring spectral lines to infer temperature, motion, and magnetic structure. The tower also played a role in standardizing solar measurements. By producing consistent observations over decades, it offered a reference point for comparing data across sites and times, a vital function in long-term solar cycle studies. In its early years, the tower faced political and financial pressures, including threats of closure. Yet its resilience mirrored the persistence of scientific inquiry. Through wars and upheavals, it stood firm, a literal and figurative beacon of continuity. As technology evolved, the Einstein Tower was surpassed by more powerful telescopes. But its historical role and symbolic significance remain unmatched. It represents the moment when physics, architecture, and solar astronomy converged. Visiting the tower today is a step into both scientific history and visionary design. Its structure feels like a frozen wave of energy, apt for a building that watches the pulsing surface of the sun. Helioseismology, the music of the sun. The sun constantly vibrates. Beneath its seemingly still surface, millions of acoustic waves ripple through the solar interior. These oscillations, though invisible to the eye, encode vital information about the sun's structure, rotation, and dynamics. This is the science of helioseismology. Much like seismologists use earthquakes to probe Earth's interior, solar physicists use these waves to map the sun. Each mode of oscillation penetrates to a different depth. By analyzing their frequencies and patterns, scientists reconstruct the sun's inner layers. The first hints of solar oscillations came from Doppler measurements of the surface, revealing rhythmic shifts in spectral lines. These shifts correspond to up and down motion caused by pressure waves, P modes, generated by convection near the solar surface. Helioseismology grew into a discipline with the advent of high-resolution, long-duration observations. Networks like GONG and space missions like SOHO's MDI and SDO's HMI provided global, uninterrupted views of oscillations across the entire solar disk. By observing wave speeds and travel times, helioseismologists constructed models of temperature, density, and sound speed inside the sun. These models confirmed and refined stellar structure theory, resolving discrepancies between predictions and observed surface behavior. One key finding was the rotation profile of the sun's interior. Unlike the surface, which rotates faster at the equator than at the poles, the radiative zone rotates more uniformly. This contrast revealed the existence of a transition layer, the tachycline, where shear and dynamo action occur. Helioseismology also unveiled subtle asymmetries in the sun's structure, such as flows, meridional circulation, and zonal bands. These patterns help explain the migration of sunspots and the mechanics behind magnetic field generation. The method extends beyond the visible side. By combining multiple acoustic signals, scientists infer features on the far side of the sun, a technique akin to sonar. This Farside helioseismology is now used for space weather forecasting. Time-distance helioseismology, a branch of the field, tracks how long it takes waves to travel between surface points. Variations in this travel time indicate subsurface structures or anomalies, such as emerging sunspots or magnetic flex regions. Another application is in understanding solar flares. Some large flares create impulsive forces strong enough to generate sunquakes, seismic waves that travel through the Sun's interior, detectable as ripples in helioseismic data. Continuous helioseismic monitoring has shown that global oscillation patterns change with the solar cycle. Frequencies shift slightly during solar maximum, reflecting changes in subsurface magnetic fields and structural properties. The Sun isn't unique in this respect. Astroseismology applies the same principles to other stars, analyzing their light curves for pulsations. This enables mass, radius, and age estimates of distant stars with remarkable precision. Helioseismology bridges solar and stellar physics. It turns the Sun into a laboratory for understanding wave propagation, magnetic feedback, and convection in plasma. Lessons that extend across the Hertzsprung-Russell diagram. The field continues to evolve with higher precision instruments and computational models. Each improvement in temporal resolution or spatial coverage reveals finer-scale dynamics within the solar interior. Light's journey time from the core to you. When you feel the Sun's warmth on your skin, the photons reaching you began their journey hundreds of thousands of years ago. Though light moves at nearly 300,000 kilometers per second in vacuum, its path from the solar core is anything but direct. Inside the Sun, light crawls. At the core, nuclear fusion converts hydrogen into helium, releasing energy in the form of high-energy gamma-ray photons. But these photons cannot escape directly. They enter a dense interior where particles absorb and re-emit them endlessly, a process called radiative diffusion. Each time a photon is absorbed and re-emitted, it changes direction randomly. This random walk turns a straight journey into a labyrinthine crawl. The typical step is only a fraction of a millimeter, and billions of steps are needed to reach the surface. Estimates vary, but most models suggest it takes between 10,000 and 170,000 years for a photon to travel from the core to the photosphere, the Sun's visible surface. This immense delay reflects the Sun's density and opacity in its inner layers. The energy, not the original photon, is what eventually reaches us. By the time light exits the Sun, it's been downshifted from gamma rays to visible and infrared light. It's a cascade of energy loss, scattering, and frequency change over vast scales. Once photons reach the photosphere, the story changes dramatically. The outer layers are transparent enough that photons travel almost uninterrupted. From there, it takes just 8 minutes and 20 seconds for sunlight to cross the vacuum to Earth. This difference highlights a key distinction. The Sun's core is not a transparent furnace, but a radiant fog. Photons are trapped and scattered endlessly, like trying to walk straight through a dense crowd that keeps redirecting you. The journey also varies depending on location. The path through the Sun's equator may differ from that through polar regions due to variations in density and magnetic field interactions, but the random walk dominates in all cases. Understanding this process helps explain why the Sun's surface brightness is so stable. The long diffusion time averages out fluctuations, acting like a low-pass filter that smooths energy release. This stability underpins the Earth's climate and life. The concept also plays a role in stellar evolution modeling. The timescale of energy transport affects how stars age, how they balance pressure against gravity, and how quickly they respond to changes in fusion rate. Modern simulations model photon transport in great detail. Monte Carlo methods are used to simulate random walks and predict emergent spectra and brightness profiles. These models are validated against helioseismic data and satellite observations. The diffusion timescale also sets a limit on how quickly the Sun could respond to changes in its core, which is to say, extremely slowly. If fusion were to change today, we wouldn't see the effect in sunlight for thousands of years. Interestingly, while photons take eons to escape, neutrinos generated in the same fusion reactions escape the core in seconds. They interact so weakly with matter that they pass through the entire Sun and Earth with minimal interaction. Radiative zone, the photon maze. The radiative zone lies between the Sun's core and its convective outer layer. It extends from about 25% to 70% of the Sun's radius and serves as the primary region for energy transport via radiation. In this zone, photons dominate the flow, but their journey is anything but swift. The plasma here is so dense that photons can't move far without interacting with particles. Each photon is absorbed and re-emitted in a new direction in a process governed by quantum electrodynamics and statistical thermodynamics. This random walk leads to a slow outward drift of energy. On average, a photon changes directions billions of times before escaping the zone. It's not the same photon that leaves, but the energy persists, cascading outward like a whispered message passed down. The temperature gradient in the radiative zone is steep, from about 15 million degrees Celsius at the core to 2 million near the top of the zone. This gradient drives the outward flow, but the process is fundamentally diffusive, not convective. Unlike the outer convection zone, there are no large-scale circulations or overturning flows here. The matter remains relatively static, stratified by pressure and temperature. Radiation, not motion, is the engine of energy transport. The zone's opacity, its resistance to light, is crucial. It's determined by the density, composition, and ionization state of the plasma. Even small changes in these properties affect how efficiently photons can migrate outward. Because of its opacity and sluggish transport, the radiative zone acts like a buffer. It damps short-term fluctuations in fusion output, ensuring the surface brightness remains stable over long timescales. It is one of the Sun's great regulators. This region also rotates more uniformly than the convective envelope. Helioseismic studies show that while the surface exhibits differential rotation, the radiative zone spins more like a solid body. This contrast is key to understanding the solar dynamo. At the interface between the radiative and convective zones lies the tachocline, a thin shear layer thought to be central to magnetic field generation. The contrast in rotation rates creates conditions for twisting and amplifying magnetic fields. Studying the radiative zone helps constrain models of stellar evolution. The efficiency of radiation transport, combined with fusion rates and boundary conditions, determines how stars age and how they transition into red giants or other stages. Observationally, we infer the radiative zone's properties through helioseismology. Sound waves that penetrate this layer reflect the internal structure, revealing density profiles, temperature gradients, and even composition variations. The radiative zone is also critical in modeling solar neutrino production. Since neutrinos are born in the core and pass through this zone almost undisturbed, understanding its structure refines predictions about neutrino flux at Earth. It's a region where time slows for light, but not for understanding. The interactions that occur here, countless and subtle, define the character of solar energy long before it reaches the surface. As dense as it is silent, the radiative zone represents the quiet middle chapter of solar energy's journey, the phase where light is trapped, reshaped, and finally allowed to proceed outward. This maze of scattering and absorption isn't chaotic. It's a highly ordered statistical regime governed by physics as fundamental as gravity itself, and it powers every heartbeat on Earth. Within this hidden layer, we find the bottleneck of sunlight, and from its depths, light rises with ancient patience, tracing paths set by physics and fate. Convective zone, the accelerating conveyor. Above the radiative zone lies the Sun's convective zone, stretching from about 70% of the solar radius to the visible surface. Here, the method of energy transport changes dramatically. Radiation gives way to convection, bulk motion of plasma rising and falling like boiling water. In this layer, the temperature is low enough and the opacity high enough that photons can no longer efficiently carry energy. Instead, heat moves through the turbulent flow of ionized gas. Hot plasma rises, cools near the surface, and sinks again in a continuous cycle. This dynamic behavior forms vast convection cells, some the size of continents and others spanning the width of entire hemispheres. The most familiar of these patterns is granulation, mottled patches on the surface, each lasting minutes and covering thousands of kilometers. The granules represent the tops of convection cells. Hot plasma from below reaches the surface, radiates energy into space, and then sinks in the darker, cooler lanes between cells. This perpetual motion transports energy quickly and efficiently to the surface. Larger structures called supergranules span tens of thousands of kilometers and persist for a day or more. These patterns drive the horizontal transport of magnetic fields and contribute to the Sun's surface dynamics. The convective zone is also the source of solar oscillations. As plasma churns, it excites pressure waves, P modes, that resonate throughout the solar interior. These oscillations are the foundation of helioseismology and our window into deeper layers. This zone plays a crucial role in the solar dynamo. Differential rotation shears magnetic field lines, while convection twists and folds them, generating the complex magnetic field that governs solar activity, including sunspots and flares. The chaotic, nonlinear nature of convective motion makes it difficult to model. Turbulence and magnetohydrodynamics interact in complex ways, requiring high-performance computing and sophisticated simulations to understand the behavior at different scales. Convection also drives solar magnetic cycles. As magnetic flux is transported and reorganized, it contributes to the periodic reversal of the Sun's global magnetic field, which occurs approximately every 11 years. Instruments like the Helioseismic and Magnetic Imager (HMI) aboard SDO observe the surface manifestations of this layer in incredible detail. Time-lapse images reveal the roiling, ever-shifting pattern of granules and flows across the solar disk. The base of the convective zone, where it meets the radiative layer, is known as the tachocline. This shear layer may be the seedbed of large-scale magnetic field generation, a place where differential rotation and stratification combine to twist fields. Though the convective zone represents only the outer third of the Sun by radius, it has a profound effect on the surface we observe. Every flare, spot, and surge of plasma begins with motions here, shaped by the interplay of heat, magnetism, and fluid dynamics. Its effectiveness as a conveyor of energy contrasts with the sluggish diffusion of the radiative zone below. Energy that took tens of thousands of years to reach this layer may take only a few weeks more to reach the surface. The efficiency of convection also supports the Sun's overall luminosity and surface stability. Though turbulent, the system self-organizes to maintain equilibrium, feeding energy upward and magnetic fields outward. Sunspots, dark yet bright. Sunspots appear as dark patches on the Sun's surface, but their darkness is relative. They are cooler than the surrounding photosphere, about 3,500 degrees Celsius compared to 5,800 degrees Celsius, and emit less light, yet they remain brighter than a full moon seen from Earth. These spots are regions of intense magnetic activity. Concentrated magnetic fields inhibit convection locally, reducing the upward transport of heat. As a result, the area cools and dims, creating the visible contrast we see as a sunspot. Sunspots are not static features. They evolve over hours to weeks, forming, growing, and decaying as magnetic fields emerge, twist, and reconnect. Large spots can span tens of thousands of kilometers, easily engulfing Earth several times over. A typical sunspot consists of two parts: the umbra, which is darkest and most magnetically intense, and the penumbra, a lighter, filamentary region surrounding the umbra. The penumbra features inclined magnetic fields and horizontal flows called evershed flows. Beneath the surface, sunspots have complex subsurface structures. Helioseismic measurements reveal how sound waves are deflected and slowed around them, offering clues to the underlying magnetic architecture and plasma flows. Sunspots usually appear in pairs or groups, reflecting magnetic bipolarity. The magnetic field lines arch out from one spot and re-enter through another. These loops store enormous amounts of energy, occasionally releasing it in flares or CMEs. Their distribution follows a well-known pattern over the solar cycle. At the start of a cycle, spots appear at mid-latitudes. As the cycle progresses, they migrate toward the equator, forming a pattern known as the butterfly diagram. The number of sunspots rises and falls in cycles of about 11 years. These cycles reflect changes in the sun's magnetic field strength and polarity. During solar maximum, sunspots are numerous and often large. During solar minimum, they may disappear entirely. Sunspots are indicators of solar activity. Periods of high sunspot numbers coincide with increased solar storms, auroras, and radiation events, phenomena that can affect satellites, radio communication, and power grids on Earth. The Maunder minimum, a period in the 17th century with very few sunspots, coincided with colder climates in parts of Europe and North America. While causation is debated, the correlation underscores the importance of sunspots as solar activity markers. Sunspots also rotate with the sun, offering a way to measure solar rotation rates. By tracking them across the disk, scientists discovered the sun's equator rotates faster than its poles, a clue to its internal fluid dynamics. Magnetic field measurements of sunspots are made using Zeeman splitting of spectral lines, a technique pioneered in early solar observatories and still used today. These readings show field strengths up to several thousand Gauss, far stronger than Earth's field. High-resolution imaging, particularly from the Daniel K. Inouye Solar Telescope, or DKIST, now reveal intricate penumbral filaments and light bridges. These features hint at the fine-scale structure of magnetic suppression and convective flow. Sunspots, while dark, are a visible signature of the sun's hidden forces. They mark places where the magnetic field wells up from the deep interior, pauses convection, and reshapes the energy emerging from below. Every sunspot is a wound in the photosphere, not of damage, but of magnetic complexity. And though they dim a part of the sun, they illuminate our understanding of its ever-changing magnetism. Flares, stellar lightning. Solar flares are sudden, intense eruptions of electromagnetic radiation from the sun's surface and atmosphere. They occur when magnetic energy built up in the solar corona is rapidly released, heating plasma to tens of millions of degrees and accelerating particles to near-light speeds. The flare process begins with magnetic reconnection. Twisted or stressed magnetic field lines suddenly break and reconnect in a more relaxed configuration. This topological rearrangement releases stored magnetic energy almost instantaneously, powering the flare's explosive effects.
The energy release spans the electromagnetic spectrum, from radio waves to gamma rays. Most of the flare's energy is emitted in extreme ultraviolet, or EUV, and X-rays, which ionize the upper layers of Earth's atmosphere and disrupt radio communications and GPS signals. Hard X-rays are produced when high-energy electrons slam into dense material in the lower atmosphere, a process known as Bremsstrahlung. At the same time, gamma rays may arise from nuclear interactions, indicating the presence of accelerated protons. Flares typically last from minutes to hours. They are classified by peak X-ray brightness in the 1 to 8 angstrom wavelength range, A, B, C, M, and X class, with X being the most powerful. Each step up indicates a tenfold increase in intensity. The most energetic flares can release over 10 to the 25 joules of energy, equivalent to millions of hydrogen bombs. However, only a fraction of that energy reaches Earth directly. Much is contained within the solar atmosphere or carried away by particles. White light flares, visible in the continuum of the optical spectrum, are rarer but particularly intense. They are thought to be associated with deep chromospheric heating and are often seen during major X-class events. Flares are often associated with active regions around sunspots where magnetic complexity and shear are highest. NOAA classifies these regions by magnetic configuration, with the most complex, delta spots, being the most flare-productive. Not all flares are accompanied by coronal mass ejections, or CMEs, but the two phenomena often coincide. When they do, the flare provides a fast, early warning, a flash of light preceding the slower-moving wave of particles. Flares also emit bursts of energetic particles, solar energetic particles, or SEPs, which can reach Earth within minutes via interplanetary magnetic field lines. These can pose risks to satellites, astronauts, and high-altitude aviation. The study of flares combines imaging, spectroscopy, and radio observations. Instruments like SDO-AIA and RESI have revealed fine-scale dynamics in flare ribbons, loops, and footpoints, offering insight into energy transport and deposition. One puzzle is how the flare energy is partitioned. What fraction goes into heating, particle acceleration, and wave generation? The details remain under investigation, but all point to a complex, multi-stage energy conversion process. Solar flares also serve as a laboratory for plasma physics. They provide natural examples of reconnection, shock formation, turbulence, and particle acceleration, phenomena that occur throughout the universe, from stars to black holes. CMEs, the delayed blow. Coronal mass ejections, or CMEs, are massive eruptions of plasma and magnetic field from the Sun's corona. Unlike the instant flash of a flare, CMEs unfold more slowly, but with enormous power. They launch billions of tons of solar material into space at high speed. A typical CME contains a tangled structure of magnetic flux ropes, twisted magnetic field lines filled with charged particles. These structures form when magnetic stress builds up in the corona, often in association with flares or filament eruptions. When the magnetic field can no longer contain the stored energy, the configuration destabilizes and explodes outward. The CME lifts off, carrying embedded magnetic fields in entrained plasma, an arc of stellar atmosphere sent into the heliosphere. CMEs vary in size and speed. Smaller events may barely reach interplanetary space, while large CMEs can exceed 3,000 kilometers per second and travel from the Sun to Earth in less than 15 hours. Most, however, take 1 to 3 days. As they propagate, CMEs expand and interact with the ambient solar wind. Their magnetic field orientations and shock fronts influence whether they compress Earth's magnetosphere or slip by harmlessly. Orientation is everything in space weather. If the embedded magnetic field is southward, opposite Earth's, it can reconnect with Earth's magnetosphere,
triggering geomagnetic storms. These storms can cause auroras, disrupt power grids, and affect satellite operations. CMEs are observed with coronagraphs, telescopes that block the sun's bright disk to reveal the faint outer corona. SOHO's LASCO and Stereo's SETCHI have captured thousands of CMEs, helping catalog their structure and direction. Halo CMEs, those expanding in all directions, appear to surround the sun in coronagraph images. These are often Earth-directed, though their symmetry can also mean they're heading away. Context from multiple spacecraft is essential. Some CMEs are stealth events with minimal low coronal signatures. Their origins are harder to trace and they challenge forecasting models. Despite lacking a dramatic flare, they can still produce significant space weather effects. The total mass ejected can exceed 10 to the 12 kilograms, comparable to the mass of Mount Everest. Combined with high speed, this gives CMEs kinetic energies rivaling the total global energy use over several days. Shock waves driven by fast CMEs accelerate particles ahead of the cloud. These solar energetic particles arrive before the bulk plasma and can damage electronics or pose radiation hazards in space. CME arrival times are forecast using heliospheric models that simulate propagation through the solar wind. Instruments like ACE and DSCO-VR at L1 provide real-time upstream measurements that refine warnings minutes before impact. The effects of a CME depend heavily on timing, orientation, and pre-existing conditions. A moderate CME can have severe consequences if it follows another event that weakened Earth's magnetic defenses, a phenomenon known as preconditioning. Auroras, the planet's neon glow. Auroras are the visible manifestation of space weather, ethereal lights dancing near Earth's poles, driven by the sun's invisible hand. When solar particles reach Earth, they follow magnetic field lines into the upper atmosphere and collide with atoms, releasing light in distinct colors. Most of these particles come from the solar wind or from coronal mass ejections. When they reach Earth, they encounter the magnetosphere, which deflects and channels them. The particles spiral along magnetic field lines toward the polar regions, creating auroral ovals. The collisions occur primarily with oxygen and nitrogen in the thermosphere, about 100 to 300 kilometers above the surface. Excited oxygen atoms emit green or red light, while nitrogen produces blue and purple hues. The specific color depends on the energy and type of interaction. Auroras usually occur in rings centered around the magnetic poles, forming the aurora borealis in the north and the aurora australis in the south. They are most common during periods of high solar activity, when more particles are ejected toward Earth. The intensity and shape of auroras vary based on the solar wind's speed, density, and magnetic orientation. A strong southward magnetic field in an incoming CME promotes reconnection with Earth's field, unleashing streams of particles and vivid auroras. Spacecraft like Themis and ground-based all-sky cameras have helped map the evolution of auroral substorms. These brief, explosive brightenings involve magnetic reconfigurations and particle injections in the near-Earth environment. Auroras are not just pretty lights, they signal deeper processes. The ionization and heating in the upper atmosphere can disrupt GPS signals, radio communication, and over-the-horizon radar, especially near polar regions. During major geomagnetic storms, auroras can expand to lower latitudes. The 1859 Carrington event caused auroras visible as far south as the Caribbean, while recent storms have brought them into continental Europe and the United States. The underlying mechanism is governed by magnetohydrodynamics, the interaction of magnetic fields and charged fluids. Earth's magnetotail stretches far behind the planet, storing energy that can suddenly release and power an auroral display. The precise triggering of substorms is still an area of active research. Models suggest a combination of magnetic reconnection, pressure buildup, and instabilities in the plasma sheet contribute to the onset and morphology of auroral outbursts. Instruments on satellites like DMSP and NOAAPOES measure particle fluxes entering the atmosphere, offering insight into auroral drivers. Coupled with ground magnetometers, they provide a full picture of space weather conditions. Auroras are also seen on other planets with magnetic fields and atmospheres. Jupiter's auroras, for instance, are driven by both solar wind and internal processes related to its moons. They demonstrate how magnetic interactions can vary across planetary systems. For indigenous cultures across the Arctic, auroras have long held spiritual significance. Modern science adds another layer of meaning, framing them as visualizations of the invisible, high-energy forces surrounding our planet. High-latitude airline flights adjust routes and radio frequencies during solar storms to mitigate risks from auroral zone ionization. These operational protocols highlight how auroras intersect with daily infrastructure in subtle but important ways. Every aurora is a cosmic dialogue, Earth's magnetosphere responding to solar whispers and shouts, and in that shimmering glow we glimpse the physics of plasma, the shape of our magnetic shield, and the sun's reach across space.